You will never reach 97% of the universe. Not in 1,000 years, not in 1,000,000,000, not if humanity builds ships that ride the edge of light speed itself. Those galaxies are already gone, not destroyed, not collapsed, just gone, slipping past a boundary that has nothing to do with distance and everything to do with the way space itself behaves when you stop paying attention to it. Right now, at this exact moment, there are galaxies racing away from Earth faster than light can travel, not because they're moving through space, but because the space between us and them is stretching, expanding, pulling the entire cosmic horizon outward like a shoreline retreating from a beach that will never see water again. And here's the part that should bother you. It's not slowing down, it's accelerating. The universe isn't just big, it's getting bigger, faster, in every direction, every second, and the rate of that expansion means that most of what exists out there, most of the matter, the stars, the galaxies we can technically see in a telescope today, we will never touch, we will never visit, we will never even send a signal to. The night sky feels infinite, but infinity has an edge, and that edge is moving. It moves at 68 kilometers per second for every megaparsec of space you try to cross, which means the farther away something is, the faster it runs. And beyond a certain point, it runs faster than physics allows us to follow. We live inside a bubble, 94 billion light-years wide, ancient, enormous, and utterly bounded, and everything outside that bubble already lost. So how does a universe this vast become unreachable? How does distance itself become the walls of a cage we didn't know we were inside? This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. Space is not empty. That's the first lie you were probably taught, and it's time we corrected it. When you look up at the night sky and see the black between the stars, your brain fills in the word nothing, a void, an absence. But intergalactic space, the gulf between galaxies, is not nothing. It's just incredibly, almost offensively sparse. There's gas out there, hydrogen mostly, some helium, traces of heavier elements scattered by dying stars and supernovae over billions of years. There's dust, there's plasma, there's dark matter, though we can't see it, only infer its presence from the way visible matter moves. And there's radiation, ancient light stretched thin by the expansion of the universe, microwaves left over from the Big Bang itself. If you could somehow stand in the middle of intergalactic space, which you couldn't because you'd be dead, you would be surrounded by all of this. But the density is so low that for practical purposes, it might as well be vacuum. A cubic meter of intergalactic space contains, on average, fewer than one atom. For comparison, a cubic meter of Earth's atmosphere at sea level contains about 10 to the power of 25 molecules, 10 with 24 zeros after it. Intergalactic space is not empty. It's just lonelier than anything your brain has a reference for. And the distances involved are worse, much worse. Before we can talk about how big the observable universe is, before we can even start to wrap our heads around the fact that most of it is already lost to us forever, we need to establish a baseline. We need to understand how astronomers measure distance at all when the thing you're trying to measure is so far away that no human will ever touch it, no probe will ever reach it, and no method you learnt in high school geometry even begins to apply. You can't pace it off. You can't drop a tape measure. You can't triangulate it the way a surveyor does with a hillside. The tools we have are light, math, and a lot of very careful guesswork. Let's start with the unit itself, a light year. Most people hear that term and assume it's a measure of time. It is not. A light year is a distance. Specifically, it's the distance light travels in 1 year through the vacuum of space. Light moves at about 299,792 kilometers per second. In more familiar terms, that's roughly 186,000 miles per second. Nothing in the universe with mass can move faster. Light sets the speed limit, and it's been obeying that limit since the universe began. Multiply that speed by the number of seconds in a year, about 31.5 million, and you get the length of 1 light year. Roughly 9.46 times 10 to the 15th meters. In miles, that's about 6 trillion. 6 trillion miles is 1 light year. And when astronomers tell you that a galaxy is 2.5 million light-years away, what they mean is that the light you are seeing tonight left that galaxy 2.5 million years ago, before humans existed, before our ancestors walked upright, before most of the ice ages that shaped the continents you live on. That light has been traveling toward you the entire time, and it's arriving right now, this second, hitting the mirror of a telescope or the retina of your eye with a message that is 2.5 million years out of date. The nearest major galaxy to the Milky Way is Andromeda, catalogued as Messier 31, sitting in the constellation Andromeda, visible to the naked eye on a dark night as a faint smudge. It doesn't look like much. It looks like a cloud. But that cloud contains roughly 1 trillion stars, twice as many as the Milky Way, and it sits 2.5 million light-years away. That is our nearest galactic neighbor of comparable size. Not the nearest galaxy overall. There are smaller dwarf galaxies much closer, but the nearest galaxy you could stand next to the Milky Way and call an equal. 2.5 million light-years. That number is going to be important because it sets the scale for everything that follows. If you can't internalize what 2.5 million light-years means, you will have no reference for what 93 billion light-years means. And if you don't understand 93 billion, you won't understand why 97% of the universe is already gone. So how do we know Andromeda is 2.5 million light-years away? Nobody flew there with a ruler. The method astronomers use depends on the distance involved, and they've built what's called the cosmic distance ladder, a series of overlapping techniques that let them step outward from our solar system to the edge of the observable universe. The first rung is parallax. If you hold your thumb up at arm's length and close one eye, then the other, your thumb appears to shift against the background. That shift is parallax, and it works because your two eyes are separated by a few centimeters, giving you two slightly different viewpoints. Astronomers do the same thing with stars, except instead of using two eyes, they use 2 points in Earth's orbit around the Sun, separated by about 300 million kilometers. Take a picture of a nearby star in January. Take another picture in July when Earth is on the opposite side of its orbit. If the star is close enough, it will appear to shift slightly against the more distant background stars. Measure that shift, apply some trigonometry, and you've got a distance. Parallax works beautifully for stars within a few hundred light-years. Beyond that, the shift becomes too small to measure accurately, even with the best instruments. So we need a new method. Enter the standard candles. A standard candle is any object whose true brightness is known. If you know how bright something actually is, and you can measure how bright it appears from Earth, you can calculate how far away it must be. The math is straightforward. Brightness falls off with the square of the distance. Double the distance, and the object appears 4 times dimmer. One of the most useful standard candles is a type of star called a Cepheid variable. These stars pulse, their brightness fluctuates in a regular, predictable pattern, and the period of that pulsation is directly related to the star's true luminosity. A Cepheid that pulses every 10 days is intrinsically brighter than one that pulses every 3 days. Measure the pulse and you know the wattage. Compare that to how dim it looks from Earth and you've got your distance. Cepheids can be spotted in galaxies up to about 20 million light-years away, which covers the local group and a bit beyond. That's how we know Andromeda is 2.5 million light-years out. Astronomers found Cepheids in Andromeda, timed their pulses, calculated their true brightness, and did the math. For galaxies farther than 20 million light-years, Cepheids get too faint. So astronomers step up to an even brighter standard candle, Type 1a supernovae. These are exploding white dwarf stars, and they're useful because they almost always explode with the same peak brightness. A white dwarf in a binary system siphons matter off its companion star until it hits a critical mass, about 1.4 times the mass of our Sun. At that point, the physics of electron degeneracy pressure gives out, the star collapses, and the resulting thermonuclear explosion is so violent and so consistent that astronomers can use it as a cosmic lighthouse. Spot a Type 1a supernova in a distant galaxy, measure how bright it looks, compare that to the known peak brightness, and you can calculate the distance out to billions of light-years. This is the method that won Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in 2011. They used Type 1a supernovae to measure the expansion rate of the universe and discovered, to everyone's surprise, that the expansion is accelerating. Something is pushing the universe apart faster and faster, and we have no idea what it is. We call it dark energy because we are very good at naming things we don't understand. The farthest objects in the universe are too distant even for supernovae to help. At those scales, astronomers rely on redshift. Light behaves like a wave, and when the source of that light is moving away from you, the wave gets stretched, the peaks spread out. For visible light, that means the color shifts toward the red end of the spectrum, hence the name. The faster something is moving away, the more its light is redshifted. And because the universe itself is expanding, galaxies at greater distances are receding faster. Measure the redshift of a galaxy's light, plug that into the equations of cosmology, and you can estimate how far away it is and how long ago the light was emitted. This method works all the way out to the edge of the observable universe, to galaxies whose light has been traveling for more than 13 billion years. Galaxies we are seeing as they existed when the universe was less than 1 billion years old. So that's the ladder. Parallax for nearby stars, Cepheids for nearby galaxies, supernovae for distant galaxies, redshift for the farthest objects we can see. Each step is calibrated against the one below it, and the whole structure is held together by decades of careful observation and cross-checking. It's not perfect. There are uncertainties at every rung, but it works. It has to work, because without it, we wouldn't know where anything is. We'd be staring up at lights in the sky with no sense of scale, no sense of structure, no way to distinguish a nearby star from a galaxy containing 100 billion suns sitting halfway across the universe. Now let's zoom out. The Milky Way is not alone. It sits inside a gravitational neighborhood called the local group, a collection of more than 50 galaxies bound together by their mutual gravity. The local group is dominated by two large spiral galaxies, the Milky Way and Andromeda, with a smaller spiral called Triangulum playing third wheel. The rest are dwarf galaxies, small irregular clumps of stars with names like the Large Magellanic Cloud, the Small Magellanic Cloud, and Leo the First. Most of them orbit either the Milky Way or Andromeda the way moons orbit a planet. The whole structure spans about 10 million light-years across, and everything inside it is gravitationally bound. That means the galaxies within the local group are not being pulled apart by the expansion of the universe. Gravity is stronger than the expansion at this scale. The galaxies are moving relative to one another, some toward us, some away, but they're not disappearing into the cosmic horizon. Not yet. Andromeda, for instance, is moving toward us, not away, toward, at about 110 kilometers per second. In roughly 4 billion years, it will collide with the Milky Way. The two galaxies will merge into a single giant elliptical galaxy that astronomers have already nicknamed Milkomeda, because scientists have a sense of humor, and also because naming things that won't happen for 4 billion years is somehow comforting. The collision won't be violent in the way you're imagining. Stars are so far apart that actual collisions between individual stars will be extraordinarily rare. But the gravitational interactions will scramble both galaxies, flinging stars into new orbits, triggering waves of star formation as gas clouds slam together, and eventually settling into a new configuration that will look nothing like either of the original galaxies. Our Sun, assuming it still exists, will likely be flung into a completely different part of the merged galaxy. If Earth survives, which is not guaranteed, the night sky will be unrecognizable. But that's a problem for a future neither you nor anyone you will ever meet will have to worry about. The local group is a calm pocket in a much larger structure. Beyond it lies the Virgo supercluster, a vast web of galaxies stretching across about 110 million light-years. The local group is just one small filament on the outer edge of that supercluster, falling slowly toward its center of mass. And beyond the Virgo supercluster lies an even larger structure called Laniakea, a supercluster of superclusters spanning 520 million light-years and containing the mass of about 100,000 Milky Ways. Laniakea is Hawaiian. It means immeasurable heaven. The name was chosen in 2014 by a team of astronomers who mapped the motions of more than 8,000 galaxies and realized they were all part of a single coherent flow, a cosmic watershed draining toward a region of space called the Great Attractor. We still don't fully understand what the Great Attractor is. We can't see it directly because it sits behind the plane of the Milky Way, hidden by dust and gas. But we can measure its gravitational pull, and we know it's enormous. Something out there, a dense knot of matter, is pulling hundreds of thousands of galaxies toward it at speeds of several hundred kilometers per second, and Laniakea is just one supercluster among millions scattered across the observable universe. This is where the numbers start to break your brain. The observable universe, the bubble of space from which light has had time to reach us since the Big Bang, is roughly 93 to 94 billion light-years across, not 13.8 billion. That's how old the universe is in years. But space itself has been expanding the entire time light was traveling toward us, so the objects whose light we're seeing today are much farther away now than they were when they emitted that light. A galaxy whose light has been traveling for 13 billion years is not 13 billion light-years away. It's more like 46 billion light-years away, because the space between us and that galaxy has been stretching the entire time. Do that calculation in all directions, and you get a sphere roughly 93 billion light-years in diameter. That's the observable universe. That's the box we're trapped in. Not by walls, but by time and the speed of light. And here's the part that should bother you. The observable universe is not the whole universe. It's just the part we can see. The actual universe, the full thing, is almost certainly much larger. How much larger, we don't know. It might be infinite, it might be finite, but so large that the observable portion is a rounding error. We have no way to measure it directly because light from beyond the observable horizon hasn't reached us yet, and depending on how fast the universe is expanding, it may never reach us. There could be entire clusters of galaxies, entire superclusters, entire regions of space larger than anything we've ever observed, sitting just outside our view, forever inaccessible, not because they're far, because the universe is expanding faster than light can cross the gap. That's not science fiction, that's cosmology. The expansion of space does not obey the speed limit that matter and light obey. Space itself can stretch faster than light can travel through it. And in the regions of the universe far enough away, that's exactly what's happening. Galaxies beyond a certain distance, about 16 billion light-years in proper distance, are receding from us faster than the speed of light. Their light is still traveling toward us, but the space between us and them is opening up faster than the light can close the gap. Some of that light will eventually reach us billions of years from now, but a lot of it won't. And every second that passes, more galaxies slip across that line. More light gets trapped on the other side of an expanding horizon that will never let it through. 97% of the galaxies in the observable universe are already beyond that line. We can still see them because the light we're detecting tonight left them billions of years ago when they were closer and the expansion was slower. But we are seeing their past, not their present. The galaxies as they exist right now, today, in this moment, are unreachable. If you pointed the most powerful rocket ever conceived at one of those galaxies and launched it at 99.9% the speed of light, it would never arrive. The space between here and there is opening faster than the rocket can cross it. You would spend eternity watching the distance grow, and it gets worse. The universe's expansion is accelerating. Whatever dark energy is, it's pushing harder now than it was a billion years ago, and it will push harder a billion years from now than it is today. That means the edge of the reachable universe is shrinking. Galaxies that are currently just inside the boundary will cross it in the future. Galaxies we can see now will fade from view as their light gets stretched into wavelengths too long for any instrument to detect. Eventually, billions of years from now, every galaxy outside the local group will disappear. The night sky will go dark except for the merged remnant of the Milky Way and Andromeda and a handful of dwarf galaxies still bound by gravity. Future astronomers, if they exist, will look up and see nothing but their own galaxy surrounded by blackness. They will have no evidence that the universe is expanding, no evidence of the Big Bang, no cosmic microwave background, because it will have been redshifted into undetectability. They will be cosmologically isolated, living in a universe that appears static and eternal, with no way to know that they are wrong. We are living in a brief window of cosmic history when the universe is old enough to be interesting and young enough to still be visible. That window is closing. And it all starts here with the 2.5 million light-years between us and Andromeda. We just established the ladder, the tools, the methods astronomers use to measure distance across scales that would make any reasonable person's head hurt. We talked about parallax and Cepheids and supernovae and redshift. We built the framework. Now we need to use it, because the first place that framework takes us is right here to our neighborhood, the local group. The name sounds modest, almost polite, like a book club that meets every third Thursday at someone's house. But the local group is the single most important structure in your entire cosmological existence, and most people have never heard of it. It is the gravitational neighborhood that contains the Milky Way, Andromeda, Triangulum, and depending on how you count, somewhere between 50 and 80 smaller galaxies, most of them dwarfs. It spans roughly 10 million light-years from edge to edge, which sounds enormous until you remember that the observable universe is 93 billion light-years across. 10 million is a rounding error, a speck, a single suburban cul-de-sac in a country the size of a continent, and yet this speck is everything. because the local group is gravitationally bound. That phrase matters more than it sounds like it should. Gravitationally bound means the galaxies inside this region are held together by their mutual attraction. Gravity, the same force that keeps you stuck to the surface of this planet, keeps the local group intact. The galaxies within it orbit a common center of mass. They move relative to one another, sometimes toward, sometimes away, but they are not being torn apart by the expansion of the universe. The expansion is still happening. Space is still stretching. But at this scale, over these distances, gravity wins. The local group is an island, a raft lashed together in the middle of an ocean that is growing wider every second. Everything inside the raft stays together. Everything outside drifts away. That is the edge, not a wall, not a border you can see, but a transition, a line in space where the math changes. Inside the local group, objects are close enough and massive enough that their gravity dominates. Outside it, the expansion of the universe dominates. Cross that line, and you are in unbound space, where galaxies are not orbiting each other but fleeing, carried apart by the stretching of space itself. Once a galaxy crosses that line, it is gone. You can still see it, at least for a while, but you cannot reach it. You cannot interact with it. You cannot send a probe, a signal, or a message that will ever arrive. The space between you and it is opening faster than anything you launch can cross it. So when astronomers say the local group represents the practical limit of our direct interaction with other galaxies, this is what they mean. Everything inside it is reachable, at least in principle. Everything outside it is not. We are stuck on this raft, and the raft is all we will ever have. Let's talk about what is on the raft. The local group is dominated by two large spiral galaxies, the Milky Way and Andromeda. Everything else is smaller, a lot smaller. Triangulum, the third largest member, is sometimes called a spiral, sometimes called irregular depending on who you ask. It contains maybe 40 billion stars. That sounds like a lot until you remember the Milky Way has somewhere between 200 and 400 billion, and Andromeda has closer to 1 trillion. Triangulum is a runt by comparison. Everything below it on the list is smaller still. Dwarf galaxies, irregular galaxies, satellite galaxies that orbit the Milky Way or Andromeda the way moons orbit a planet. The Large Magellanic Cloud and the Small Magellanic Cloud are visible from the southern hemisphere with the naked eye. They look like detached pieces of the Milky Way, which in a sense they are. They orbit us. They are being slowly torn apart by our gravity, shedding streams of stars and gas that will eventually be absorbed into the Milky Way's outer halo. There are dozens more you have never heard of. Sculptor, Fornax, Leo I, Leo II, Draco, Ursa Minor. Most of them contain only a few million stars, maybe a few tens of millions. Some are so dim and so diffuse that they were not discovered until the 1990s, despite being practically in our backyard. A galaxy called Segue 1, discovered in 2006, contains only about 1,000 stars. 1,000. You could count them if you had the patience. For comparison, the globular cluster Omega Centauri, which orbits inside the Milky Way and is not a galaxy, contains about 10 million stars. Segue 1 is so faint that it barely qualifies as a galaxy at all. But it has dark matter, lots of it. The visible stars are just the tip of an invisible iceberg, a halo of dark matter holding the whole structure together. Without that dark matter, the stars would have drifted apart billions of years ago. Segue 1 exists because something we cannot see is holding it together, and we only know that because the stars that are there are moving faster than they should be if only their own gravity mattered. This is a recurring theme in the local group. Most of the mass is invisible. The galaxies you can see, the stars and gas that show up in photographs, represent only about 15% of the total mass. The rest is dark matter, whatever that is. We know it is there because galaxies rotate too fast. Stars at the outer edges of spiral galaxies are moving so quickly that they should fly off into space, the way a stone flies off a sling if you spin it too hard. But they do not. Something is holding them in, something with mass, something with gravity, something that does not emit light or absorb light or interact with normal matter in any way we can detect except gravitationally. We call it dark matter because we have to call it something, and because admitting we have no idea what most of the universe is made of does not look good on a grant application. The total mass of the local group, including all the dark matter, is about 2 × 10⁻12 solar masses, 2 trillion suns. Most of that mass is split between the Milky Way and Andromeda. They are the 2 heavyweight anchors holding the whole structure together. Everything else is either a satellite orbiting one of them or a smaller independent galaxy drifting in the space between. And the space between is not empty. There is gas out there. Hydrogen mostly, some ionized, some neutral, some gathered into faint clouds, some scattered so thin that a cubic meter contains fewer than 1 atom. There is a faint haze of light from stars that have been stripped out of their parent galaxies by tidal forces and now wander alone in intergalactic space. We call them intragroup stars, and there are billions of them, exiled from their homes, drifting in the dark with no galaxy to call their own. Andromeda is moving toward us. That deserves repeating because it is one of the few examples in the entire universe where something is getting closer instead of farther away. Almost every galaxy outside the local group is redshifted, meaning its light is stretched toward the red end of the spectrum because it is moving away from us. Andromeda is blue-shifted. Its light is compressed, shifted toward the blue because it is approaching. The closing speed is about 110 kilometers per second. That is roughly 250,000 miles per hour. Andromeda is racing toward the Milky Way faster than any object humans have ever built, and there is nothing anyone can do to stop it. In roughly 4 billion years, the 2 galaxies will collide. Collide is a misleading word. Galaxies are mostly empty space. The stars are so far apart that the chance of any 2 stars actually hitting each other during the merger is effectively 0. You could fire the entire Milky Way through Andromeda like a bullet through a cloud, and almost nothing would touch. But gravity does not care about empty space. Gravity reaches. As the 2 galaxies approach, their gravitational fields will start to distort each other. Tidal forces will stretch and twist both galaxies, pulling stars out of their orbits, flinging some into intergalactic space, dragging others toward the merging cores. Gas clouds will slam together, compressing and heating until they ignite in a furious wave of star formation. Millions of new stars will be born in the span of a few 100 million years, far faster than the normal background rate. The night sky, if anyone is still around to see it, will be spectacular. Bright blue giants everywhere, some of them so massive they will burn out and explode as supernovae within 10 million years of forming. The 2 supermassive black holes at the centers of the Milky Way and Andromeda will spiral toward each other, shedding energy by gravitational radiation, and eventually merge into a single black hole weighing something like 80 million solar masses. The merger itself will take a few billion years to complete. The galaxies will swing past each other, pull back, swing past again, losing energy with each pass, until they finally settle into a single elliptical galaxy. Astronomers have already given it a name, Milkomeda, because naming things that will not happen for 4 billion years is oddly comforting. Our sun will probably survive. Probably. It will be flung into a new orbit somewhere else in the merged galaxy. If Earth is still around, which is not guaranteed, the night sky will be completely unrecognizable. No Milky Way, no band of light arcing overhead. Just a scattering of stars in random directions, most of them much farther apart than they are now, because elliptical galaxies are puffier than spirals, less organized. Ellipticals are what you get when you take two spiral galaxies, smash them together, and let gravity scramble the result. All the careful structure, the spiral arms, the organized rotation gets erased. What you are left with is a cloud of stars in a roughly spherical or football-shaped distribution, with no coherent rotation, no plan, no memory of what came before. But that is 4 billion years away. Right now, today, the local group is stable, mostly. Triangulum is doing its own thing, orbiting somewhere in the space between the Milky Way and Andromeda, possibly on its way toward a future collision of its own. The dwarf galaxies are slowly being cannibalized. The Sagittarius dwarf elliptical galaxy, discovered in 1994, is currently in the process of being torn apart by the Milky Way's gravity. It has already made several passes through the Milky Way's disk, and each time it does, it loses more stars. In a few billion years, it will be gone completely, absorbed, erased. The same fate awaits most of the other dwarf galaxies. They are too small to resist. They orbit, they lose mass, they fade, and eventually they disappear. The Milky Way and Andromeda are not just the largest galaxies in the local group. They are the survivors. They got big by eating everything smaller. This is how galaxies grow. Mergers, cannibalism. There is no other way. A galaxy cannot simply accumulate gas from intergalactic space and grow smoothly over time. There is not enough free gas, and even if there were, the rate of accumulation would be far too slow. If you want to build a galaxy the size of the Milky Way, you need to start with something smaller and let it eat its neighbors. That is the standard model. Every large galaxy is the product of hundreds or thousands of smaller mergers stretching back to the early universe. The Milky Way itself is a graveyard. If you could rewind time and trace the orbits of every star in the Milky Way's outer halo backward, you would find that most of them did not originate here. They came from dwarf galaxies that merged with us billions of years ago. Their original structures have been erased, but the stars remain, scattered across the halo like forensic evidence of ancient crimes. Astronomers call these remnants stellar streams, and they are everywhere. Faint rivers of stars tracing the paths of dead galaxies. The Milky Way is not a single coherent object. It is a patchwork, a collage, a mass grave of everything it has consumed. The local group, then, is not a static picture. It is a dynamic system, constantly evolving, constantly rearranging itself under the pull of gravity. And it is also, in a very real sense, the edge of everything we will ever be able to reach. The boundary is not sharp. There is no line in space with a sign that says you are now leaving the local group. But there is a transition, a region where the math changes. Inside the local group, gravity dominates. Galaxies orbit each other. They interact. They merge. Outside the local group, the expansion of the universe dominates. Galaxies recede. They do not orbit. They simply move away, carried by the stretching of space itself, and they move faster the farther out you look. The boundary, such as it is, sits at about 3 to 5 million light-years from the center of mass of the local group, depending on which direction you measure. Beyond that, galaxies are no longer bound. The nearest major galaxy outside the local group is probably Maffei 1, a giant elliptical sitting about 10 million light-years away, hidden behind the plane of the Milky Way. We did not even know it existed until 1968, because the dust in our own galaxy blocks most of the light. Maffei 1 is not part of the local group. It is not gravitationally bound to us. It is receding, slowly, carried away by the expansion of the universe. We will never interact with it. We will never merge with it. It is outside the raft, adrift in the current. And this is where the real isolation sets in, because the local group is not just the edge of what we can reach. It is the edge of what future civilizations will be able to reach. Imagine a spacefaring species 1 billion years from now. They wake up in a galaxy, maybe ours, maybe one of the others in the local group, and they start exploring. They build ships. They travel to nearby stars, nearby galaxies. Eventually they map the entire local group. And then they look outward, toward the rest of the universe, and they discover something uncomfortable. Everything outside the local group is moving away, not slowly, faster than their ships can travel, faster than light itself can cross the gap. They can see distant galaxies through their telescopes, sure, but those galaxies are ghosts. The light they are detecting left those galaxies billions of years ago. The galaxies as they exist right now, in the present, are even farther away, receding even faster, and there is no way to catch them. Every calculation they run, every simulation they build, tells them the same thing. They are stuck. The local group is their prison, not because they lack the technology to leave, but because the universe itself will not let them. That is the situation we are in right now. We just have not fully processed it yet because we are still in the phase where the universe looks large and full and accessible. We can still see galaxies billions of light years away. We can still detect the cosmic microwave background, the afterglow of the Big Bang. We can still piece together the history of the universe from the light that has reached us. But all of that light is old. Some of it is more than 13 billion years old. The universe it is showing us is not the universe that exists today. It is a memory, a photograph. And the longer we wait, the more of that light will fade. The galaxies we see now will dim as their light gets stretched into wavelengths too long to detect. The cosmic microwave background will redshift into nothingness. Eventually, billions of years from now, the only galaxies visible in the night sky will be the ones in the local group. Everything else will have disappeared beyond the horizon, and there will be no evidence left that the universe was ever larger than the 10 million light-years we can still see. Future astronomers, if they exist, will look up and conclude that the universe is small, static, and eternal. They will have no way to know they are wrong. No way to know that their ancestors, us, lived in a time when the universe was still visible in all its immensity. They will be cosmologically isolated, and they will not even know what they are missing. We are living in a brief golden age of cosmology. The universe is old enough to have developed structure, galaxies, stars, planets, civilizations capable of asking questions. And it is still young enough that the answers are visible. That window is closing, not tomorrow, not in your lifetime, not even in the lifetime of this planet, but it is closing, and the local group is the floor beneath our feet, the raft we are standing on, the edge of everything we will ever touch. Beyond it lies the cosmic web, the great voids, the structures that connect galaxy clusters across hundreds of millions of light-years, the scaffolding of the universe itself, and all of it is drifting away. We have just established the local group, the gravitational raft we are standing on, the 10 million light-year bubble that represents everything humanity will ever be able to touch. Inside that bubble, gravity wins. Galaxies orbit each other, interact, merge. Outside it, the expansion of the universe wins. Galaxies recede, they do not orbit, they flee. And the farther out you look, the faster they go. But between here and there, between the local group and the edge of the observable universe, there is structure. Not the kind of structure you are used to, not buildings, not planets, not even individual galaxies scattered randomly like seeds thrown across a field. The universe on large scales does not look random at all. It looks planned, organized, woven. Astronomers call it the cosmic web, and once you see it, you cannot unsee it. Picture a sponge, not a kitchen sponge, the rectangular synthetic kind, but a natural sea sponge, irregular, organic, full of holes. The solid part of the sponge is thin, thread-like, forming a network of interconnected strands. The holes are everywhere, some small, some enormous, and they take up most of the volume. Now scale that sponge up to 93 billion light-years and replace the solid threads with galaxies, hundreds of billions of them stretched along filaments that span hundreds of millions of light-years. That is the cosmic web. Galaxies are not spread evenly through space. They are concentrated in long, thin structures, like beads on a string, with vast empty regions in between. The filaments are where the action is. They are the densest parts of the web, the places where galaxies cluster together, pulled by gravity into narrow threads that stretch across the universe. Where filaments intersect, you get galaxy clusters, the largest gravitationally bound structures in the universe. Some clusters contain thousands of galaxies packed into a region only a few million light-years across. The Virgo cluster, the nearest major cluster to the local group, contains more than 2,000 galaxies. The Coma cluster, about 300 million light-years away, contains over 1,000. These are the nodes, the knots in the web, the places where the structure is most obvious. But the filaments and clusters, as impressive as they are, represent only a small fraction of the universe's volume. Most of the space, the overwhelming majority of it, is empty. Not empty the way intergalactic space within a galaxy cluster is empty, with a few atoms per cubic meter and the occasional stray photon. Empty in a way that makes intergalactic space look crowded. These regions are called cosmic voids, and they dominate the universe. Depending on how you measure, voids occupy somewhere between 80 and 90% of the known volume of space. 90%. The universe is not mostly galaxies. It is not mostly stars or gas or even dark matter in any concentrated sense. It is mostly nothing. Voids, gaps, holes in the web where almost nothing exists. The existence of voids was suspected as early as the 1970s when astronomers began mapping the positions of galaxies in 3 dimensions. Measuring a galaxy's position on the sky is easy. You take a picture, note where it shows up, but that only gives you 2 dimensions. To get the third, the depth, you need to measure the galaxy's redshift. The more redshifted a galaxy is, the farther away it is and the faster it is receding due to the expansion of the universe. Measure enough redshifts, plot the galaxies in 3-dimensional space, and the structure reveals itself. Galaxies are not scattered randomly. They line up. They form walls, sheets, filaments, and between those structures there are gaps, big ones. The first major void was discovered in 1981 by a team led by Robert Kirshner, an astronomer at the Harvard-Smithsonian Center for Astrophysics. Kirshner and his colleagues were conducting a redshift survey of galaxies in the direction of the constellation Boötes, a faint constellation in the northern sky. They expected to find galaxies distributed more or less evenly, maybe with some clumping here and there. What they found instead was a hole, a region of space roughly 330 million light-years across, centered about 700 million light-years from Earth, that contained almost no galaxies, not a few galaxies, almost none. They counted about 60 galaxies in a volume that should have contained closer to 2,000. 60 galaxies in 330 million light-years. Think about that. The local group, our gravitational neighborhood, spans about 10 million light-years and contains at least 50 galaxies, possibly as many as 80, depending on how generously you count the dimmest dwarfs. 10 million light-years, 50 galaxies. Now scale that up by a factor of 33. 330 million light-years. If galaxies were distributed evenly, you would expect thousands of them. Kirshner's team found 60. The void was not completely empty, but it was close enough that it earned a nickname, the Great Nothing. The formal name is the Boötes Void, and it remains one of the largest and most prominent voids ever discovered. 330 million light-years across. Some sources give the radius as about 62 megaparsecs, which translates to roughly 200 million light-years, putting the full diameter closer to 400 million depending on where you draw the boundaries. Either way, the scale is absurd. You could fit the entire local group inside the Boötes Void thousands of times over and still have room left. You could fit the Virgo supercluster, all 110 million light-years of it, inside the void with space to spare, and it would still feel empty, because there is almost nothing there. The discovery was unsettling. Not because voids themselves were unexpected, they were predicted by simulations of large-scale structure formation, but because the Boötes Void was so large and so empty that it strained the models. If the universe started out smooth, as the cosmic microwave background suggests, with only tiny density fluctuations seeded in the first fraction of a second after the Big Bang, how do you grow something this empty this fast? Gravity pulls matter together. It does not push it apart. Over time, dense regions should get denser and underdense regions should get emptier, yes, but the process should be gradual. The Boötes Void looked like someone had scooped out a chunk of the universe and forgotten to fill it back in. To understand how voids form, you need to go back to the beginning. In the first few 100,000 years after the Big Bang, the universe was hot, dense, and almost perfectly smooth. Almost. There were tiny fluctuations in density, variations of about 1 part in 100,000. Some regions had slightly more matter than average. Some had slightly less. These fluctuations were quantum in origin, tiny ripples in the fabric of space-time that got stretched to cosmic scales during a period of rapid expansion called inflation. When the universe cooled enough for atoms to form, those fluctuations froze into the structure of space. Slightly denser regions had slightly stronger gravity. They pulled in more matter. Over millions of years, those regions grew denser still, pulling in even more matter. Gravity is a runaway process. The rich get richer. Meanwhile, the underdense regions, the places that started out with slightly less matter than average, lost what little they had. The matter drifted away, pulled toward the denser regions nearby. Over time, the underdense regions became voids, not because something pushed the matter out, but because gravity pulled it away. The denser regions collapsed into filaments and clusters. The underdense regions emptied out. By the time the universe was a few billion years old, the cosmic web had taken shape: filaments, clusters, and voids, threads, nodes, and holes. That is the structure we see today, and it all traces back to those tiny fluctuations in the first fraction of a second after the Big Bang. The voids are not perfectly empty. Deep surveys with modern telescopes have found a few galaxies scattered inside even the largest voids. Faint dwarf galaxies mostly, small irregular clumps of stars that somehow avoided being pulled into the surrounding filaments. These void galaxies are strange. They tend to be younger, bluer, and more gas-rich than galaxies in denser regions. They have fewer heavy elements, less chemical enrichment, because they have had fewer interactions with other galaxies. No mergers, no collisions, no gravitational harassment from neighbors. They have been evolving in isolation, slowly converting their gas into stars at a rate much lower than galaxies in clusters or filaments. Some of them may have formed relatively recently, within the last few billion years, long after most of the universe's star formation had already peaked and begun to decline. Void galaxies are the hermits of the cosmos, quiet and undisturbed, living out their lives in the emptiest places in the universe. But even with a few galaxies scattered here and there, voids remain profoundly empty. The average density inside a void is about 10 to 20% of the average density of the universe as a whole. That means if you took a random cubic megaparsec of space, a box about 3.3 million light-years on a side, and counted up all the matter inside it, galaxies, gas, dark matter, everything, you would get some number. Now take the same sized box and drop it into the middle of a void. You would get 10 to 20% of that number. The rest is just missing. It is not hidden. It is not in some exotic form we cannot detect. It is somewhere else, pulled away by gravity billions of years ago, piled up in the filaments and clusters that surround the void like the walls of a bubble. The Boötes Void is not unique. It is just famous because it was one of the first, and because it is unusually large and empty even by void standards. Astronomers have since catalogued thousands of voids across the observable universe. Some are smaller, only 50 or 100 million light-years across. Some are comparable to the Boötes Void. A few are larger. The largest known void, sometimes called the Giant Void or the Eridanus supervoid, spans about 1 billion light-years. 1 billion. That is 100 times the diameter of the local group. It is larger than the Virgo supercluster. It is so large that light takes 1 billion years just to cross from one side to the other, and it is mostly empty. The existence of voids this large raises questions. If the universe started out smooth and structure grew gradually over time through the pull of gravity, there should be a limit to how empty a region can get and how large a void can grow before the expansion of the universe and the influence of dark energy smooth things out. The biggest voids we see are right at the edge of that limit, maybe even slightly past it depending on which models you trust. Some cosmologists have argued that the largest voids are evidence that something about our understanding of structure formation is incomplete. Maybe the initial density fluctuations were not as smooth as we thought. Maybe dark matter behaves slightly differently on very large scales. Maybe dark energy is not perfectly uniform, and its strength varies slightly from place to place, affecting how fast different regions expand. These are not mainstream ideas, but they are out there, floated by researchers trying to reconcile the observations with the theory. The voids themselves are useful. They are not just empty space to be ignored, they are cosmological probes. Because voids are so underdense, they are less affected by the messy, nonlinear physics that governs galaxy formation and evolution. Galaxies collide, merge, form stars, blow out gas in supernova-driven winds, get shaped by black holes and radiation and magnetic fields. It is a mess. Voids, by contrast, are quiet. The matter inside them has barely been processed. It has not been stirred up by interactions or heated by shocks or enriched by stellar nuclear synthesis. Voids preserve a cleaner record of the initial conditions, the primordial density field that existed shortly after the Big Bang. By studying the shapes and sizes and distribution of voids, cosmologists can test models of how structure formed, how dark matter is distributed, and how the expansion of the universe has evolved over time. One of the most interesting features of voids is that they expand faster than the rest of the universe. That sounds strange, but it makes sense if you think about it. The expansion of the universe is not uniform. It is the same rate everywhere on average, but locally, gravity can slow it down or even reverse it. Inside a galaxy cluster, gravity is strong enough that the cluster is not expanding. The galaxies are gravitationally bound, orbiting a common center of mass, held together despite the expansion of space around them. Inside a void, the opposite happens. There is so little matter, and therefore so little gravity, that nothing is holding the expansion back. Space inside a void expands slightly faster than the average, not a lot faster. The difference is small, but over billions of years it adds up. Voids grow. They push the surrounding filaments and clusters farther apart. In a sense, the voids are driving the large-scale expansion of the cosmic web, inflating like balloons and carrying the walls of the sponge outward. This has consequences. As voids expand, the galaxies on their edges get pulled along. Some galaxies that were once part of a filament end up isolated, cut off from their former neighbors, drifting alone in the expanding emptiness. Other galaxies that were close to a void's edge get pushed toward nearby clusters, accelerating their infall and increasing the rate at which clusters grow. The cosmic web is not static, it is dynamic, constantly rearranging itself under the competing influences of gravity and expansion. The voids are a major part of that story. The contrast between voids and filaments could not be starker. Stand in the middle of a void if you could, and look around. You would see almost nothing. A few faint smudges of light, distant dwarf galaxies, maybe a handful within 100 million light-years. Beyond that, darkness. The nearest large galaxy might be 200 million light-years away, a faint speck barely visible even with a telescope. The cosmic microwave background would be there, the faint glow of the Big Bang stretched into microwaves, but that is uniform in all directions. It does not tell you where you are. For all practical purposes, you would be alone in the dark. Now move to a filament, galaxies everywhere. Not scattered randomly, but lined up, stretched along a thread that might run for hundreds of millions of light-years. Some of the galaxies are spirals like the Milky Way. Some are ellipticals, bloated and red and old. Some are irregular, messy clumps of stars that have not settled into any coherent shape. The filament would be crawling with structure, galaxies and galaxy groups, and the faint diffuse glow of intergalactic gas lit up by radiation from nearby stars and black holes. If you followed the filament long enough, it would lead you to a cluster, and at the cluster the density would spike. Thousands of galaxies packed into a region only a few million light-years across, moving at hundreds or thousands of kilometers per second, held together by gravity wells so deep that not even light can escape from the supermassive black holes lurking at the centers of the largest galaxies. The difference between a void and a filament is the difference between an empty highway at 3 in the morning and the floor of the New York Stock Exchange at the opening bell. Same universe, completely different environments. The cosmic web is not just a pretty picture. It is the scaffolding that holds the universe together. Everything we see, every galaxy, every star, every planet, exists because of the web. Matter fell into the filaments. Filaments collapsed into galaxies. Galaxies formed stars. Stars formed planets. Planets formed, in at least one case, life. The structure we see today is the reason anything exists. If the universe had been perfectly smooth, with no density fluctuations, no seeds for structure to grow from, there would be no galaxies. Just a thin, uniform fog of hydrogen and helium expanding forever, cooling, dimming, fading into darkness. The fluctuations, those 1 part in 100,000 variations in the early universe, were the difference between a universe full of structure and a universe with none. The voids, the filaments, the clusters, all of it traces back to those initial ripples. And the voids, as empty as they are, play a critical role. They are the low notes in the symphony, the rests between the chords. Without them, the web would collapse into a single uniform density. There would be no filaments, no clusters, no contrast. The voids define the structure by being absent from it. They show you where the matter is not, which is just as important as knowing where it is. The Boötes Void, the great nothing, is a reminder of how unevenly the universe is put together. We live in a filament, on the edge of the local group, near a cluster, surrounded by other galaxies. Our view is biased. We see density because we are in a dense region, but most of the universe is not like this. Most of it is empty, quiet, dark. If you picked a random point in the observable universe and dropped yourself there, the odds are overwhelming that you would land in a void. You would see almost nothing. No galaxies nearby, no stars, no planets, just the faint glow of the cosmic microwave background and the distant, unreachable filaments scattered across the horizon like cities seen from the middle of a desert. The cosmic web is the largest structure in the universe, larger than any single object, larger than any cluster or supercluster, larger than anything bound by gravity. It spans the entire observable universe, 93 billion light-years. Every galaxy we can see is part of it. And it is transient. The web is not permanent. It is not stable. It is held together by a balance between gravity, which pulls matter into filaments and clusters, and the expansion of the universe, which pulls everything apart. Right now, gravity is winning on small scales. Galaxy clusters are stable. Filaments are intact. But on larger scales, expansion is winning. Superclusters are not gravitationally bound. The filaments are being stretched. The voids are growing. And as the universe continues to expand, accelerating under the influence of dark energy, that balance will shift. Gravity will lose. The web will come apart. Billions of years from now, the voids will have expanded so much that the filaments will be stretched thin, the clusters isolated, the galaxies scattered. The structure we see today, the beautiful, intricate web of filaments and voids, will be gone, erased by expansion. Future civilizations, if they exist, will look up and see a much emptier universe than we do. The web will have dissolved, the voids will have won, but that is a problem for later. Right now, the web is still here, the filaments still connect the clusters, the voids are still growing, but slowly. And the entire structure is being carried along by something much larger and much stranger than gravity. The expansion of space itself, the ghost driver, the force that is pulling the universe apart faster than anything inside it can move. And it has been accelerating for the last 5 billion years. We have just walked through the cosmic web, the great scaffolding of filaments and voids that stretches across the observable universe. We have seen the Boötes Void, 330 million light-years of almost nothing, and we have seen the filaments where galaxies cluster like beads on a string. We have established the structure. Now we need to understand what is pulling that structure apart. Because the universe is not static, it is not sitting still, it is expanding. Every second of every day, the space between distant galaxies is growing larger, and the force driving that expansion, the ghost behind the wheel, is something we do not understand at all. This is not a new discovery. The expansion of the universe was established nearly a century ago by a man named Edwin Hubble, an astronomer working at the Mount Wilson Observatory in California in the 1920s. Hubble was not the first person to suggest the universe might be expanding. That honor belongs to a Belgian priest and physicist named Georges Lemaitre, who proposed the idea in 1927 based on Einstein's equations of general relativity, but Lemaitre's work was published in a French journal and largely ignored. Hubble was the one who provided the observational proof, and Hubble was the one who got the credit. That is how science works. You can have the idea, but if you cannot show the data, the idea does not stick. Hubble's proof came from measuring the light of distant galaxies, not their brightness, their color, specifically the wavelength of specific absorption lines in their spectra. When you pass the light from a star or a galaxy through a prism or a diffraction grating, you get a spectrum, a rainbow of colors from blue to red. But that rainbow is not smooth. It is interrupted by dark lines, absorption lines, where specific wavelengths of light have been absorbed by elements in the star's atmosphere. Hydrogen absorbs light at specific wavelengths. So does helium, calcium, sodium, and every other element. Each element leaves its own fingerprint in the spectrum. By looking at those fingerprints, you can identify what a star is made of, even if it is sitting on the other side of the galaxy. Hubble was not looking at individual stars, he was looking at entire galaxies, and he noticed something strange. The absorption lines in the spectra of distant galaxies were shifted toward the red end of the spectrum, not by a little, by a lot. The hydrogen line that should have appeared at a wavelength of 656 nanometers in the blue-green part of the spectrum was showing up at 670, 680, 700 nanometers deep into the red. The entire spectrum had been stretched, shifted toward longer wavelengths. Astronomers call this redshift, and by the late 1920s, Hubble had measured it in dozens of galaxies. Redshift by itself was not surprising. It had been observed before. What Hubble did that no one else had done was measure the distances to those galaxies and plot the redshift against the distance. The distances were rough, based on a technique involving Cepheid variable stars and a lot of assumptions that turned out to be wrong, but they were good enough. Hubble found a pattern. The farther away a galaxy was, the more its light was redshifted. Not a random correlation, a straight line. Double the distance, double the redshift. Triple the distance, triple the redshift. The relationship was linear, clean, unmistakable. Hubble published his findings in 1929 in a paper that is now one of the most cited works in the history of astronomy. The universe, he concluded, is expanding. The relationship Hubble discovered is now called Hubble's law, and it can be written as a simple equation. The recession velocity of a galaxy, the speed at which it appears to be moving away from us, is equal to the Hubble constant multiplied by the distance to that galaxy. The Hubble constant is a number that describes the rate of expansion. In modern measurements, it is about 68 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. So for every 3.26 million light-years you look outward, galaxies are receding 68 kilometers per second faster. Look twice as far, and they are receding 136 kilometers per second faster, 3 times as far, 204 kilometers per second faster. The farther out you go, the faster galaxies are moving away. That sounds simple. It is not. Because the first instinct, the gut reaction most people have when they hear this, is to picture galaxies as objects flying through space, moving away from us the way a ball flies away from you after you throw it. That picture is wrong. Galaxies are not moving through space. Space itself is expanding, and the galaxies are being carried along with it. This is one of the hardest concepts in cosmology to internalize because it contradicts everything your everyday experience tells you about how motion works. When you throw a ball, the ball moves and the space around it stays still. When a car drives down a highway, the car moves and the highway stays put. That is how motion works in your life. That is not how motion works in the universe. Space is not a fixed background. It is not a stage. It is a thing, a physical entity that can stretch, bend, warp, and expand. General relativity, Einstein's theory of gravity, describes space and time as a four-dimensional fabric that responds to the presence of mass and energy. Mass warps space. That warping is what we experience as gravity. But space can also expand or contract on its own, driven not by the motion of objects through it, but by the properties of space itself. On the largest scales, across distances of hundreds of millions of light-years, space is stretching. The fabric is being pulled taut, and everything embedded in that fabric is being carried along. Galaxies are not moving. The space between them is growing. This distinction matters because it explains something that would otherwise be impossible. Some galaxies, the ones far enough away, are receding from us faster than the speed of light. Faster than light. That sounds like a violation of the rules. Einstein's special relativity says nothing can move through space faster than light, and that is still true. Nothing is moving through space faster than light. But space itself can expand as fast as it wants. There is no speed limit on the expansion of space. A galaxy sitting 46 billion light-years away is not moving through space at all. It is sitting still in its local patch of space. But the space between us and that galaxy is expanding so fast that the distance is growing at a rate equivalent to several times the speed of light. The galaxy is not breaking the rules, space is. Here is an analogy that might help. Imagine you are standing on a conveyor belt, a long one, stretching off into the distance. You are not walking, you are standing still. But the belt is moving, carrying you along. Now imagine someone else is standing on the same belt, 100 meters ahead of you. They are also standing still relative to the belt. But because the belt is moving, the distance between you and them is growing. You are receding from each other, not because either of you is walking, but because the belt is carrying you apart. Now imagine the belt is stretching, not just moving, but getting longer. Every meter of belt expanding into 2 meters, then 3, then 4. You are still standing still. So is the other person. But the distance between you is growing faster and faster, and eventually it is growing so fast that even if you started running toward them at your maximum speed, you would never catch up. The belt is stretching faster than you can run. That is cosmic expansion. The galaxies are standing still. The space between them is stretching. And on the largest scales, it is stretching faster than light can cross the gap. Edwin Hubble did not understand this, not fully. In his 1929 paper, he interpreted the redshift as a Doppler shift, the same effect that makes the pitch of an ambulance siren drop as it drives past you. He thought the galaxies were moving through space, and the motion was stretching the light waves the way motion stretches sound waves. That picture works locally, within galaxy clusters, where galaxies really are moving through space relative to each other, but it breaks down on larger scales. The redshift of distant galaxies is not a Doppler shift. It is a cosmological redshift caused by the expansion of space itself, stretching the light waves as they travel. Hubble did not have the framework to understand that. General relativity was still new. The idea that space could expand was bizarre, even to Einstein, who initially rejected it. Hubble had the data, he had the pattern, but he did not have the full explanation. The explanation came later, built by a generation of physicists and astronomers who took Einstein's equations seriously and followed them to their logical conclusions. If space is expanding now, it must have been smaller in the past. Wind the clock back far enough, and the universe must have been denser, hotter, more compressed. Keep going, and you reach a point where the entire observable universe was squeezed into a region smaller than an atom. That is the Big Bang, not an explosion in space, but an expansion of space, the moment when the universe began. The evidence for it is everywhere. The cosmic microwave background, the afterglow of the Big Bang, is still detectable today, stretched into microwaves by 13.8 billion years of expansion. The abundance of hydrogen and helium in the universe matches the predictions of Big Bang nucleosynthesis, the first few minutes when the universe was hot enough to fuse protons into helium nuclei. And the large-scale structure of the universe, the cosmic web, the filaments and voids, all of it traces back to tiny quantum fluctuations in the first fraction of a second after the Big Bang, fluctuations that were stretched to cosmic scales during a brief period of exponential expansion called inflation. The Big Bang model works. It explains the observations. It makes predictions that have been tested and confirmed again and again, but it also raises a question. If the universe is expanding, what is driving the expansion? In the early universe, the answer was straightforward. The universe was full of matter and radiation, and both of those things have gravity. Gravity pulls, it does not push. So you would expect gravity to slow the expansion over time, the way Earth's gravity slows a ball you throw into the air. For decades, that was the assumption. The universe is expanding, but the expansion is slowing down. Eventually, maybe it will stop. Maybe it will even reverse, and the universe will collapse back into a big crunch, the opposite of the Big Bang. That was the prediction. It was wrong. In 1998, two independent teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, announced results that stunned the field. They had been measuring the distances to Type 1a supernovae in distant galaxies, using those supernovae as standard candles to map the expansion history of the universe. What they found was that distant supernovae were dimmer than expected, not by a little, by enough to matter. The dimness meant the supernovae were farther away than they should have been if the expansion of the universe had been slowing down. The only way to explain the observations was to conclude that the expansion is not slowing down, it is speeding up. The universe is expanding faster now than it was a billion years ago, and it was expanding faster a billion years ago than it was 2 billion years ago. Something is pushing the universe apart, and that something has been getting stronger over time. No one knows what it is. Astronomers call it dark energy because they had to call it something, and because admitting that 70% of the universe is made of something we know absolutely nothing about does not inspire confidence. Dark energy is not a particle, it is not a field in the traditional sense. It is not radiation, it is not matter, it is something else, something with the bizarre property that it has negative pressure. Positive pressure pushes outward, the way the air in a balloon pushes against the walls. Negative pressure pulls inward, the way a stretched rubber band pulls back. Except in general relativity, negative pressure has a weird side effect. It causes space to expand. The more dark energy there is, the faster space expands. And because space is expanding, there is more volume, which means more dark energy, which means faster expansion. It is a runaway process. Dark energy is accelerating the expansion of the universe, and the acceleration is itself accelerating. The leading candidate for what dark energy might be is something called the cosmological constant, a term that Einstein added to his equations of general relativity in 1917 and later called his biggest blunder. Einstein added the term because he wanted the universe to be static, not expanding or contracting, and his equations without the constant predicted that the universe could not be static. It had to be either expanding or collapsing. So he added a fudge factor, a constant that represented a kind of intrinsic energy density of space itself, a vacuum energy that pushed outward and balanced the inward pull of gravity. When Hubble discovered the universe was expanding, Einstein realized the constant was unnecessary and removed it. Turns out he was wrong to remove it. The constant, or something very much like it, appears to be real. Space does have an intrinsic energy density, and that energy density is what we now call dark energy. The problem is that when you try to calculate what that energy density should be based on quantum field theory, you get an answer that is off by a factor of 10 to the power of 120 orders of magnitude. That is not a rounding error. That is the worst prediction in the history of physics. No one knows how to fix it. The alternative is that dark energy is not a constant. It is a field, something dynamic that changes over time, something that might have been weaker in the past and could be stronger in the future. Astronomers call this idea quintessence, and it has the advantage of being flexible enough to fit the data without predicting absurd values for the vacuum energy. The disadvantage is that there is no direct evidence for it, no detection of a quintessence field, no theoretical framework that explains where it comes from or why it exists. Quintessence is a name attached to an idea that may or may not describe reality. Dark energy, cosmological constant, quintessence, they are all placeholders, labels for something we do not understand. What we do know is that dark energy makes up about 68% of the total energy density of the universe. Dark matter, the invisible stuff that holds galaxies together, makes up about 27%. Normal matter, the stuff you are made of, the stuff stars and planets and gas clouds are made of, makes up about 5%. 5%. Everything you have ever seen, touched, or interacted with, every atom in your body, every photon that has ever hit your eye, every star in the night sky, represents 5% of the universe. The rest is dark, hidden, unknown. And the largest component of that unknown is the thing that is tearing the universe apart. The analogy most often used to explain cosmic expansion is rising bread dough. Imagine you are baking a loaf of bread. You mix the dough, knead it, let it rise. As the yeast ferments, it produces carbon dioxide gas, and the gas forms bubbles inside the dough. The dough expands. Now imagine you are an ant standing on the surface of one of those bubbles. From your perspective, the dough around you is moving away in all directions. If there is another ant on a different part of the same bubble, that ant is also seeing the dough move away in all directions. Neither ant is at the center. There is no center. Every point on the surface of the dough is equivalent. The dough is expanding, and every ant sees the same thing. Ants farther away are receding faster because there is more dough between them, and all of that dough is expanding. That is cosmic expansion. The galaxies are the ants. Space is the dough. There is no center, there is no edge. Everything is moving away from everything else, not because anything is moving through space, but because space itself is expanding. Another analogy is a balloon with dots drawn on it. Inflate the balloon, and the dots move apart. The dots are not sliding across the surface of the balloon. They are fixed to the rubber, and the rubber is stretching. The farther apart two dots are, the faster the distance between them grows, because there is more rubber between them and all of that rubber is stretching. The balloon analogy has a weakness. It implies there is an inside and an outside, a three-dimensional space that the two-dimensional surface is embedded in. The universe does not have an outside. It is not embedded in anything, but the analogy works for illustrating how expansion carries objects apart without requiring them to move. The expansion rate, the Hubble constant, is not actually constant. It changes over time. In the early universe, when the density of matter and radiation was much higher, the expansion was faster. As the universe expanded and the density dropped, the expansion slowed. Then, about 5 billion years ago, something changed. Dark energy, which had been a minor component up to that point, became dominant. Matter dilutes as the universe expands. The density of matter drops because the same amount of mass is spread over a larger volume. Dark energy does not dilute. If dark energy is a property of space itself, then as space expands and the volume increases, the total amount of dark energy increases. More space, more dark energy. Eventually, dark energy overtook matter and the expansion started accelerating. That acceleration has been ongoing ever since, and it will continue as long as dark energy remains dominant, which appears to be forever. The Hubble constant is about 68 kilometers per second per megaparsec. That is the current expansion rate. But there is a catch. When you measure the Hubble constant using different methods, you get different answers. Measure it using the cosmic microwave background, the afterglow of the Big Bang, and you get about 67. Measure it using Cepheid variable stars and Type Ia supernovae in nearby galaxies, the method Adam Rees and his team use, and you get about 73. That is a 6 km per second per megaparsec difference, and it has been stubbornly persistent for more than a decade. Some astronomers think it is a measurement error, that one method or the other is biased in a way we have not accounted for. Others think it is real, that the tension between the two measurements is telling us something important about the universe, something that the standard model of cosmology is missing. Maybe dark energy is not constant. Maybe it was stronger in the past, or weaker, or behaving in a way that affects how we interpret the early universe. Maybe there is new physics hiding in the gap between 67 and 73, or maybe someone just screwed up the calibration and the whole crisis will evaporate when the next generation of instruments comes online. No one knows. The Hubble tension, as it is called, is one of the most contentious issues in cosmology right now, and it matters because the Hubble constant is not just a number. It is the clock that tells you how fast the universe is expanding, how old it is, how big the observable universe is, and how much of it is already out of reach. The expansion of space is not something you can feel. It does not affect you. It does not affect the Earth, the solar system, the Milky Way, or even the local group. Gravity is stronger than expansion on those scales. The Earth is not expanding. You are not expanding. The atoms in your body are held together by electromagnetic forces that are vastly stronger than the stretching of space. The solar system is held together by the sun's gravity. The Milky Way is held together by the combined gravity of hundreds of billions of stars and a supermassive black hole at its center. The local group is held together by the mutual gravity of the Milky Way, Andromeda, and the smaller galaxies orbiting them. None of those structures are expanding. Expansion only dominates on scales larger than a few tens of millions of light-years, where the distances are so vast and the matter so spread out that gravity cannot hold things together anymore. That is where space takes over. That is where the expansion starts to matter. And on those scales, the expansion is relentless. A galaxy cluster 100 million light-years away is receding at about 2,000 kilometers per second. A galaxy a billion light-years away is receding at roughly 20,000 kilometers per second. A galaxy 10 billion light-years away is receding faster than the speed of light. You cannot see that galaxy as it is now. You can only see it as it was 10 billion years ago, when the light you are detecting tonight first left it. The galaxy has since moved farther away, carried by the expansion of space, and it is still moving faster and faster, accelerating into the distance. The light it is emitting right now, today, will never reach us. It is aimed in our direction, but the space between us and that galaxy is opening faster than the light can cross it. The photons are running on a treadmill that is accelerating away from them. They will never catch up. That is the ghost driver. Not a force you can see, not a particle you can detect, not even a field you can point an instrument at and measure. Just a property of space itself, a built-in tendency to expand, accelerating, unstoppable, pulling the universe apart 1 megaparsec at a time. It has been driving since the beginning. It will keep driving long after every star has burned out and every galaxy has faded from view. The universe is not winding down towards some equilibrium state. It is accelerating towards something else, something colder, emptier and darker than anything we have a good analogy for. The expansion will not stop. It will not reverse. It will not slow down. If dark energy remains constant, or if it strengthens over time as some models suggest, the universe will expand forever, faster and faster, until every galaxy outside the local group has disappeared beyond the horizon and the night sky is empty except for the faint glow of the cosmic microwave background, stretched into wavelengths so long that no instrument will ever detect it again. Edwin Hubble discovered the expansion in 1929, and we have been trying to understand it ever since. We know it is happening. We know it is accelerating. We know dark energy is driving it. We do not know what dark energy is, where it came from, or why it exists. We do not know if the Hubble constant is really 67 or 73, or if the difference between those two numbers is hiding something fundamental that our current models are missing. We do not know if the expansion will continue forever, or if something will change, some new phase transition, some shift in the properties of space that will alter the future in ways we cannot predict. What we do know is that the expansion is not optional. It is built into the fabric of the universe, and it has consequences, big ones, because the faster space expands, the more of the universe becomes unreachable. Galaxies we can see now are already beyond the point where we could ever send a signal that would reach them. Most of the observable universe is already lost, and the boundary of what we can reach is shrinking every second. That boundary has a name, the cosmic event horizon, and understanding it requires understanding something deeply uncomfortable. That light, the fastest thing in the universe, the thing we use to see everything beyond our atmosphere, is not fast enough. There are regions of space where light itself cannot catch up to the expansion, and those regions are growing fast. We have just met the ghost driver, the mysterious force pulling the universe apart faster and faster with every passing second. We have seen how space itself expands, carrying galaxies along with it, stretching the fabric of reality like rising dough or an inflating balloon. We have learned that this expansion is accelerating, driven by something we call dark energy, something that makes up 68% of the universe and yet remains completely unexplained. And we have established that this expansion is not something you can feel or measure in your daily life because gravity dominates on the scales that matter to you. The Earth is not expanding. The solar system is not expanding. Even the local group, our 10 million light-year gravitational neighborhood, is not expanding. But beyond that, space takes over, and the farther out you look, the faster everything is moving away. Now we need to confront the part that breaks most people's brains, the part that sounds like a mistake, like someone misunderstood the rules, like the universe is cheating. Some galaxies, the distant ones, the ones sitting billions of light years away, are receding from us faster than the speed of light, faster than light. And before you start composing an angry email about how Einstein said nothing can go faster than light, let me stop you. Einstein was right. Nothing can move through space faster than light. That rule has not been broken. That rule cannot be broken. It is built into the structure of space-time itself. But space itself is not bound by that rule. Space can expand as fast as it wants, and in the farthest reaches of the observable universe, space is expanding so fast that galaxies embedded in it are being carried away from us at speeds that make light look slow. This is not a loophole. This is not a technicality. This is the difference between motion through space and the expansion of space itself. When a car drives down a highway at 60 miles per hour, it is moving through space. The space between the car and the point it started is not growing. The car is changing its position within a fixed spatial framework. That is motion. When a galaxy 10 billion light-years away recedes from us at twice the speed of light, it is not moving through space. It is sitting still in its local patch of space. But the space between us and that galaxy is growing, stretching, inflating, and the rate at which new space is being added between here and there is so high that it corresponds to a recession velocity greater than the speed of light. The galaxy is not violating the rules. Space is playing a different game entirely. Let me give you an analogy. Imagine you are standing on a moving walkway at an airport, one of those motorized conveyor belts that carries you along while you stand still. You are not walking, you are just standing there, letting the belt do the work. Someone else is standing on the same belt 50 meters ahead of you. They are also not walking, but the belt is moving, so the distance between you and them is staying constant. Now imagine the belt starts stretching. Every meter of belt is expanding into 2 meters, then 3, then 4. You are still standing still. So is the other person. But the distance between you is growing, and it is growing faster the more belt there is between you. If the belt is stretching fast enough, the distance between you could be growing at 10 meters per second, 20 meters per second, 100 meters per second. You are not moving, they are not moving, but the distance is increasing faster than you could ever run. That is what is happening with galaxies. They are standing still in their local frames of reference. The space between us is stretching, and the amount of new space being added every second is so large that the recession velocity exceeds the speed of light. This effect has a name. Cosmologists call it the Hubble flow, and it is a direct consequence of the uniform expansion of space described by general relativity. The recession velocity of a galaxy is proportional to its distance. Double the distance, double the recession velocity. The relationship is linear, at least to a good approximation over most of the observable universe. The proportionality constant is the Hubble constant, about 68 kilometers per second per megaparsec. A megaparsec is roughly 3.26 million light-years. So for every 3.26 million light-years you look outward, galaxies are receding 68 kilometers per second faster. At 10 megaparsecs, the recession velocity is 680 kilometers per second. At 100 megaparsecs, 6,800 kilometers per second. At 1,000 megaparsecs, 68,000 kilometers per second. Keep going. At about 14,000 megaparsecs, roughly 46 billion light-years, the recession velocity equals the speed of light. Beyond that distance, galaxies are receding faster than light can travel, and there is nothing special about that distance. It is not a wall, it is not a boundary in any physical sense. It is just the point where the math crosses a threshold. The speed of light in a vacuum is 299,792 kilometers per second. Call it 300,000 to keep the numbers manageable. If a galaxy is far enough away that the space between us is expanding at 300,000 kilometers per second, then light leaving that galaxy and heading in our direction is fighting a losing battle. The light is traveling toward us at 300,000 kilometers per second through its local space. But the space between us and the galaxy is opening at the same rate, 300,000 kilometers per second. The photon is running on a treadmill, making no progress. If the expansion rate is even slightly higher, the photon loses ground. It is aimed at us, traveling at the maximum speed the universe allows, and it is moving away from us, not because the photon is moving backward, because the space it is trying to cross is stretching faster than it can traverse it. This is where the concept of the cosmic event horizon comes in. The event horizon is the boundary beyond which light emitted today will never reach us. Not because the light stops existing, not because something blocks it, because the expansion of space is too fast. The photon will travel forever through space, always aimed in our direction, always moving at the speed of light, and it will never arrive. The distance between the photon and Earth will grow larger every second, not smaller, because space is being added faster than the photon can cross it. The cosmic event horizon is not a place. It is a limit, a line in space-time that separates the region we can ever interact with from the region we cannot. Anything inside the horizon can, in principle, send us a signal that will eventually arrive. Anything outside the horizon cannot. If you are standing just outside the horizon and you shine a flashlight at Earth, the beam will never get here. The photons will travel for billions of years, always moving toward us, and they will spend eternity falling farther behind. The location of the cosmic event horizon depends on the expansion history of the universe and the properties of dark energy. If dark energy is a cosmological constant, a fixed property of space that does not change over time, then the event horizon sits at a distance of about 16 billion light-years in proper distance, the distance measured right now accounting for the expansion of space. That number is smaller than the 46 billion light-year radius of the observable universe, and that difference is critical. The observable universe is defined by the light that has already reached us. It includes galaxies whose light has been traveling for billions of years, emitted when the universe was younger and those galaxies were much closer. The cosmic event horizon is defined by the light that could reach us in the future. It includes only the galaxies close enough that light emitted today or in the future can eventually catch up to us. Despite the ongoing expansion, everything beyond the horizon is lost. We can still see it, at least for now, because we are detecting old light emitted billions of years ago when those galaxies were closer, but we will never see those galaxies as they are now. We will never receive any new information from them. They are gone. Here is the uncomfortable part. Most of the galaxies we can see are already beyond the cosmic event horizon. Not most of the volume, most of the galaxies. If you point a telescope at a random patch of sky and count the galaxies you can detect, the vast majority of them are so far away that they are already unreachable. The light we are seeing tonight left those galaxies billions of years ago when the expansion was slower and they were closer. In the time it took that light to reach us, the galaxies themselves have been carried farther away by the accelerating expansion of space. They are now beyond the horizon. If you wanted to send a message to one of those galaxies, a radio signal, a laser beam, anything, it would never arrive. The signal would travel outward at the speed of light, making steady progress through space, and the distance to the target galaxy would grow faster than the signal could close the gap. You would be firing a bullet at a target that is accelerating away from you faster than the bullet can fly. The bullet does not stop. It does not turn around. It just never catches up. The fraction of the observable universe that is beyond the cosmic event horizon depends on how you define the observable universe and how you measure distances. But the popular number, the one that shows up in headlines and YouTube videos and gets passed around without much scrutiny, is 97%. 97% of the galaxies we can see are already beyond the horizon. 97% of the observable universe is already lost. That number is a simplification, and depending on exactly how you calculate it, you can get slightly different answers, but the basic conclusion is sound. The overwhelming majority of the universe we can observe is already out of reach. We can see it because we are looking at the past, but we cannot interact with it. We cannot send probes, signals, or messages. We cannot visit. We cannot explore. It is gone. Let me be clear about what that means. When you look at a galaxy 10 billion light-years away, you are seeing it as it was 10 billion years ago. The light hitting your eye or your telescope tonight left that galaxy when the universe was only 3.8 billion years old. In the 10 billion years since that light was emitted, the galaxy has been carried farther away by the expansion of space. It is now much farther than 10 billion light-years. The exact distance depends on the details of the expansion history, but a reasonable estimate puts it somewhere around 30 billion light-years away in proper distance. That galaxy, as it exists right now, is beyond the cosmic event horizon. Light leaving that galaxy today will never reach us. We can still see it, but only in the past. The galaxy could explode into a supernova tomorrow, and we would not know for billions of years. By the time the light from that explosion reaches us, if it ever does, the galaxy will be even farther away, and the light from the moment after the supernova will already be too late to catch up. We are seeing ghosts, echoes, memories of galaxies that are no longer where we see them, and may no longer exist in any form we would recognize. Now let me make it worse. The cosmic event horizon is not static. It is shrinking. Every second, galaxies that were just inside the horizon cross over to the outside. They slip beyond the point where light emitted now could ever reach us. The boundary is not moving toward us in space. It is moving backward in time. Galaxies that are currently just barely reachable will become unreachable as the expansion accelerates. Future astronomers, billions of years from now, will have a smaller observable universe than we do. They will see fewer galaxies, they will receive less light, and eventually they will see almost nothing. Let me walk you through what happens. Right now, we can see galaxies out to a distance of about 46 billion light-years, the radius of the observable universe. That sphere contains roughly 2 trillion galaxies, give or take an order of magnitude depending on how you count the smallest dwarfs. Most of those galaxies are faint, distant, and visible only in deep exposures taken by space telescopes like Hubble or the James Webb Space Telescope. Some are so far away that their light has been traveling for more than 13 billion years, emitted when the universe was less than 1 billion years old. We can see them because the light has had enough time to reach us, but we are running out of time. As the universe continues to expand and the acceleration continues, the light from those distant galaxies will get stretched into longer and longer wavelengths. The galaxies will appear redder, dimmer, cooler. Eventually, their light will be stretched so far into the infrared and then into the radio spectrum that no telescope we can build will be able to detect it. The galaxies will fade from view, not because they stop emitting light, but because the light gets stretched beyond the point where our instruments can pick it up. The observable universe will shrink. In about 100 billion years, give or take, the only galaxies still visible will be the ones in the local group. The Milky Way, Andromeda, Triangulum, and whatever dwarf galaxies have not been cannibalized by then. By that point, the Milky Way and Andromeda will have merged into a single giant elliptical galaxy. Let us call it Milkomeda. Future astronomers living in Milkomeda will look up at the night sky and see their own galaxy, a scattering of stars, and beyond that, nothing. No other galaxies, no clusters, no filaments, no cosmic web. The observable universe, from their perspective, will consist of one galaxy surrounded by darkness. They will have no evidence that other galaxies ever existed. They will have no evidence that the universe is expanding. The cosmic microwave background, the afterglow of the Big Bang, will have been redshifted into oblivion, stretched into wavelengths so long that it will be indistinguishable from the random thermal noise of empty space. Future astronomers will have no way to detect it, no way to measure it, no way to know it ever existed. They will look up and conclude reasonably that the universe is small, static, eternal, and consists of one galaxy. They will be wrong, but they will have no way to know they are wrong. All the evidence that would tell them otherwise will have faded beyond detectability. The expansion of the universe will have carried everything else beyond their cosmic event horizon, and they will be cosmologically isolated, trapped in a single galaxy with no knowledge of the larger universe that surrounds them. They will invent theories to explain the stars and the structure of their galaxy, and those theories will be incomplete because they will be missing the critical context that comes from observing the rest of the cosmos. They will be doing cosmology in a dark room with no windows. We are lucky. We are living in a brief window of cosmic history when the universe is old enough to have structure, galaxies, stars, planets, and life, and young enough that the evidence of the Big Bang and the expansion of the universe is still visible. We can still see the cosmic microwave background. We can still detect galaxies billions of light years away. We can still piece together the history of the universe from the light that has reached us. But that window is closing. It is not closing fast, not on human timescales, not even on the timescale of the lifetime of our sun. But it is closing, and the cosmic event horizon is the line that marks the edge of the window. Everything beyond it is already gone, and more is crossing that line every second. The analogy that works best for me is a river with a waterfall. Imagine you are standing on the bank of a river, upstream from a massive waterfall. The water is flowing past you toward the edge. You can see boats drifting along with the current, some close to you, some farther away. The boats closer to the waterfall are moving faster because the current is stronger there. Eventually, a boat gets close enough to the edge that the current is so strong the boat cannot escape even if it fires its engine at full power. That point, the point of no return, is the event horizon of the waterfall. Once a boat crosses that line, it is going over the edge. It does not matter how powerful the engine is, the current is too strong. You can still see the boat for a while after it crosses the horizon, at least until it goes over the edge and disappears. But you cannot interact with it anymore. You cannot throw it a rope. You cannot radio it a warning. It is gone. The cosmic event horizon works the same way. Galaxies beyond the horizon are like boats past the point of no return. They are still out there, still emitting light, still moving through their local space. But the current of cosmic expansion is so strong that nothing they emit can ever reach us. The light they send in our direction is traveling at full speed, the cosmic equivalent of an engine at full power, but the current is faster. The light is being carried backward, away from us, despite moving toward us through space. It will never arrive. Now let me address the obvious question. If the cosmic event horizon is at about 16 billion light-years, and the observable universe extends to 46 billion light-years, why can we see galaxies that are already beyond the horizon? The answer is that the light we are seeing was emitted in the past when those galaxies were closer. Light does not care about the current position of the galaxy that emitted it. It only cares about the position the galaxy was at when the light started its journey. A galaxy that is now 30 billion light-years away, well beyond the horizon, was much closer 10 billion years ago when the light we are detecting tonight was emitted. At that time, the galaxy was inside the region from which light could eventually reach us. The light left, started traveling toward us, and spent billions of years crossing the expanding space between us. By the time the light arrives, the galaxy has moved farther away. It is now beyond the horizon, but the light is already here. It made the trip. The problem is that no new light from that galaxy will ever reach us. The light it is emitting now, today, is starting from a position beyond the horizon, and it will never catch up. We are seeing the last photons that will ever arrive from that galaxy. Once those photons are gone, once the light emitted when the galaxy was still inside the reachable region has all been received, that galaxy will disappear from view. We will stop getting updates. The last image we will ever have of that galaxy will be frozen in time, a snapshot from billions of years ago, and that is all we will ever know about it. This is already happening. There are galaxies visible in deep Hubble images, faint red smudges near the edge of detectability, that are so far away that the light we are seeing is billions of years old. Those galaxies are now beyond the cosmic event horizon. They have slipped past the boundary. The light we are detecting tonight is ancient, emitted when the universe was young and those galaxies were closer. In a few billion years, that light will have all arrived. There will be no more photons left in transit, and those galaxies will fade from view, not because they stop existing, but because the stream of information from them has run dry. The universe will have carried them so far away that their light cannot reach us anymore. They will become invisible, erased from our observable universe, forgotten. The 97% figure, the claim that 97% of the universe is already lost, comes from comparing the volume inside the cosmic event horizon to the volume of the observable universe. The observable universe is a sphere with a radius of about 46 billion light-years. The cosmic event horizon is a sphere with a radius of about 16 billion light-years. The volume of a sphere scales with the cube of the radius. So the volume inside the event horizon is proportional to 16 cubed, about 4,000. The volume of the observable universe is proportional to 46 cubed, about 97,000. Divide 4,000 by 97,000 and you get about 4%. Subtract from 100 and you get 96%. Round up slightly depending on the exact values you use for the distances and you get 97%. 97% of the volume of the observable universe is beyond the cosmic event horizon. We can see it, we cannot reach it, it is lost. That number is not exact. It is a rough estimate based on simplified assumptions about the expansion history and the properties of dark energy. If dark energy is not a cosmological constant, if it changes over time, the numbers shift slightly, but the conclusion does not. The overwhelming majority of the universe we can observe is already beyond the point where we can interact with it. Most of the galaxies we can see are ghosts. We are looking at the past, and the present is out of reach. The cosmic event horizon is not a wall, it is not a surface. It is not a place you could travel to and touch. It is a limit, a boundary in space-time that separates cause from effect. Events inside the horizon can affect us. Light, signals, particles, anything emitted inside the horizon can eventually reach us. Events outside the horizon cannot. They are causally disconnected. They exist, but they exist in a part of the universe that is no longer part of our universe in any meaningful sense. We can see their past, but we cannot interact with their present or their future. They are gone. And the boundary is moving. Every second, more galaxies cross the horizon, more information is lost, more of the universe slips beyond our reach. The expansion is accelerating, driven by dark energy, and as long as that acceleration continues, the cosmic event horizon will continue to shrink. Future astronomers will have access to less information than we do. They will see fewer galaxies, detect fewer photons, and have a harder time reconstructing the history of the universe. And eventually, billions of years from now, they will see almost nothing. One galaxy, darkness, and no evidence that anything else ever existed. We are living in the golden age of cosmology, the age when the universe is still visible, the age when the evidence is still here, still detectable, still within reach. And that age is ending, slowly on a timescale so long that no human civilization will live to see the transition, but ending nonetheless. The cosmic event horizon is the edge of everything we will ever be able to touch, and it is shrinking. The light from distant galaxies is fading. The universe is disappearing. Not because it is dying, but because it is running away from us, faster than we can follow, faster than light itself can chase it. And there is nothing anyone can do to stop it. We have just established the cosmic event horizon, the boundary beyond which light emitted today will never reach us, no matter how long we wait. We have seen how the expansion of space carries distant galaxies away faster than light itself can travel through that space, not because the galaxies are moving, but because the space between us is stretching. We have learned that 97% of the observable universe is already beyond that horizon, already lost, visible only as ghosts from the past, frozen in time at the moment their light began its journey billions of years ago. And we have established that the horizon is shrinking, that more galaxies cross that line every second, slipping beyond the point where any future light they emit could ever catch up to us. That was the physics. Now we need to talk about what it means, because the cosmic event horizon is not just an abstract boundary on a cosmologist's diagram. It is the edge of everything that will ever matter to anyone, anywhere, at any point in the future. And that edge is closing. The universe is not dying. Let me be clear about that before we go any further. Stars are still forming. Galaxies are still colliding and merging. Black holes are still feeding. Supernovae are still exploding. The universe is not running out of fuel, at least not yet, and it will not for a very long time. The problem is not that the universe is fading because it is winding down. The problem is that the universe is fading because it is running away. The expansion of space, driven by dark energy, is accelerating. It has been accelerating for the last 5 billion years, and as far as we can tell, it will keep accelerating forever. And as it accelerates, the light from distant galaxies gets stretched, the wavelengths get longer, visible light shifts into the infrared, then into microwaves, then into radio waves, then into wavelengths so long that no instrument we can build will ever detect them. The galaxies do not stop shining. They just disappear from view, their light stretched beyond the point where it registers as light at all. This is already happening, not in some distant hypothetical future, right now, today. The most distant galaxies we can see, the ones whose light has been traveling for more than 13 billion years, are so redshifted that their ultraviolet light, the bright blue glow of young hot stars, has been stretched all the way into the infrared. The James Webb Space Telescope was built specifically to detect those galaxies because Hubble could not see them. Hubble's instruments were optimized for visible and near-infrared light. The most distant galaxies had been redshifted so far that they were invisible to Hubble's cameras. Webb's instruments are tuned to longer wavelength, deeper into the infrared, and that is why Webb can see galaxies that Hubble missed. Not because Webb is more powerful in some abstract sense, though it is, but because Webb is looking at the right part of the spectrum. The galaxies were always there. They were just hidden, their light stretched into wavelengths Hubble was not designed to detect. Now imagine that process continuing, not for decades or centuries, but for billions of years. The expansion keeps accelerating, the galaxies keep receding, Their light keeps getting stretched. Eventually, even Webb's instruments would not be able to detect them. You would need a telescope optimized for even longer wavelengths, deeper into the radio spectrum. Build that telescope and you could still see the galaxies, at least for a while. But the process does not stop. The light keeps stretching. Eventually, the wavelengths get so long that the photons carry almost no energy. They are still photons, technically, but they are so stretched out, so diluted by the expansion of space, that detecting them becomes impossible. Not impossible because the technology is not good enough. Impossible because there is no technology that could work. The signal gets lost in the noise. The galaxies fade. Not because they stop emitting light, but because the light stops being detectable. They become invisible, erased from the observable universe by the relentless stretching of space. This is what astronomers mean when they say the universe is fading. It is not that the stars are going out. It is that the light from distant stars is being stretched into oblivion. The universe as a whole is still bright, still full of energy, still full of galaxies and stars and all the machinery of cosmic structure. But the part of the universe we can see is shrinking. The observable universe, the bubble of space from which light has had time to reach us, is not getting smaller in terms of its radius. That radius is still growing, slowly, as light from farther and farther away finally completes its journey. But the number of galaxies inside that bubble is dropping. Galaxies that were visible a billion years ago have faded from view, their light stretched beyond detectability. Galaxies that are visible today will fade a billion years from now. The universe is not emptying out. Our view of it is emptying out. The curtain is closing, and we are sitting in the audience watching the lights go down one by one. There is another piece to this, and it is worse. The fading is not just about distant galaxies disappearing into the infrared. It is also about the fact that the universe is making fewer new stars. Star formation peaked about 10 billion years ago when the universe was roughly 3 billion years old. That was the era when galaxies were forming stars at the highest rate, churning out new suns faster than at any other point in cosmic history. Since then, the rate has been declining, slowly at first, then faster. Today, the universe is forming stars at about 3% of the peak rate. 3%. The decline is not because galaxies are running out of gas. There is still plenty of hydrogen out there, the raw material for star formation. The decline is happening because the gas is not collapsing into stars the way it used to. Galaxies are aging. They are settling down. The chaotic, violent mergers that trigger bursts of star formation are becoming rarer as the universe expands and galaxies get farther apart. The gas that remains is getting hotter, more diffuse, harder to compress, and in many galaxies, supermassive black holes at their centers are pumping out so much energy that they are heating the gas and preventing it from cooling and collapsing. The black holes are acting as thermostats, keeping the temperature too high for star formation to proceed efficiently. The result is that stars are dying faster than they are being replaced. Old stars, the ones that formed billions of years ago, are reaching the ends of their lives and fading. Low-mass stars like our Sun swell into red giants, blow off their outer layers, and leave behind white dwarfs, dim embers that will glow faintly for trillions of years before cooling into darkness. High-mass stars explode as supernovae, leaving behind neutron stars or black holes, objects that emit little or no visible light. The bright blue stars, the ones that dominate the light output of young galaxies, have lifetimes of only a few million years. They burn fast and die young. As those stars disappear and fewer new ones form to replace them, galaxies get dimmer, redder, older. The spiral arms, the bright regions of active star formation that make galaxies like the Milky Way so striking in photographs, fade away. the galaxies become dominated by old red stars, low-mass dwarfs that will burn for tens of billions of years but give off very little light. A survey published in 2015 measured the total light output of more than 200,000 galaxies across a wide range of distances and wavelengths. The study used data from 7 different telescopes, covering 21 different wavelengths from the ultraviolet to the far infrared. The goal was to get a complete census of how much light the universe is producing, how that light is distributed across different wavelengths, and how it has changed over time. The results were striking. The universe today is producing about half as much light as it was 2 billion years ago. Half. The decline was even steeper in the past. Between 2.25 billion years ago and 750 million years ago, the light output dropped by about 40%. The universe is dimming, not because individual stars are fading, but because the total number of bright stars is declining. Fewer stars are being born. More stars are dying. The net result is that the universe is getting darker. The lead author of that study, an astronomer named Simon Driver at the University of Western Australia, put it plainly: the universe is slowly fading away. That phrase, fading away, got picked up by the press and turned into headlines that made it sound like the universe was on its deathbed, which is not quite right. The universe is not dying in the sense of running out of energy or collapsing or approaching some kind of heat death, at least not yet. But it is fading in the sense that the total amount of light being emitted by galaxies is declining, and that decline will continue for as long as star formation keeps dropping. Eventually, tens of billions of years from now, star formation will stop almost completely. The last generation of stars will form, burn and die, and after that no new stars will replace them. The galaxies will go dark, one by one, until the only light left comes from the faint glow of white dwarfs and the occasional flare from matter falling into a black hole. But we are getting ahead of ourselves. That is the far future, the deep future. The era when the universe is 100 billion years old or more. Right now, the universe is only 13.8 billion years old. It is young. It is still full of stars, still full of light, still full of structure. The problem we are facing is not that the universe is running out of stars. The problem is that the universe is running away from us, and the light from most of it is being stretched into wavelengths we cannot detect. Combine the two effects, the decline in star formation and the redshifting of distant light, and you get a double blow. The universe is producing less light, and the light it is producing is harder to see. The observable universe is not just shrinking in terms of the number of galaxies we can detect. It is also dimming in terms of the total amount of light reaching us. We are losing galaxies from the far edge of the observable universe as they fade into the infrared, and we are losing light from the galaxies that remain as they age and their star formation declines. The night sky is getting emptier and darker, and it will keep getting emptier and darker for as long as the expansion continues. Now let me walk you through what happens in the future. Not the near future, not the time scale of human civilizations or even the lifetime of our sun, but the deep future, the cosmological future, the time scale on which galaxies evolve and the structure of the universe changes. Right now, we can see roughly 2 trillion galaxies scattered across the observable universe. That number is an estimate, and it depends on how you count the faintest dwarfs. But 2 trillion is the figure that gets quoted most often. Most of those galaxies are faint, distant, and visible only in deep exposures taken by space telescopes. Some are so far away that their light has been traveling for more than 13 billion years. We can see them because the light has had time to reach us. But as the universe continues to expand and the acceleration continues, those galaxies will fade from view. not because they are destroyed, not because they stop existing, but because their light gets stretched beyond the point where we can detect it. The galaxies disappear from our observable universe, erased not by any physical process but by the geometry of space-time and the relentless expansion driven by dark energy. In about 100 billion years, give or take, the only galaxies still visible from Earth, or from wherever humans or their descendants or their successors happen to be, will be the ones in the local group. The Milky Way, Andromeda, Triangulum, and whatever dwarf galaxies have not been absorbed by then. By that point, the Milky Way and Andromeda will have merged into a single giant elliptical galaxy. Astronomers have already given it a name, Milkomeda. The merger will take a few billion years to complete, starting in about 4 billion years when the two galaxies make their first close pass. After the merger, Milkomeda will be the only large galaxy visible. Everything else, every galaxy outside the local group, every cluster, every filament, every piece of the cosmic web, will have faded from view, not because those structures stopped existing, but because the light from them has been redshifted into oblivion. The expansion of space will have carried them so far away that the light they emit can no longer reach us. The observable universe will have shrunk to a single gravitationally bound island, a few trillion stars in a sea of darkness. Future astronomers, if they exist, will look up at the night sky and see Milkomeda, a scattering of stars, closer together than the stars in our current night sky because elliptical galaxies are more compact than spirals, but still recognizable as stars. Beyond that, nothing, no spiral galaxies in the distance, no clusters, no faint smudges of light marking the locations of other galaxies, just darkness, empty space. The cosmic microwave background, the afterglow of the Big Bang, will still be there, but it will have been redshifted so far into the radio spectrum that it will be indistinguishable from the random thermal fluctuations of empty space. Future telescopes will not be able to detect it. Future astronomers will have no evidence that the Big Bang ever happened. They will have no evidence that the universe is expanding. They will have no evidence that other galaxies exist or ever existed. They will look at the stars in their own galaxy and conclude, reasonably, that the universe consists of one galaxy surrounded by infinite empty space. They will invent cosmologies to explain the stars and the structure of their galaxy, and those cosmologies will be wrong, but they will have no way to know they are wrong. All the evidence that would tell them otherwise will have faded beyond detectability. This is not speculation. This is extrapolation. It is what happens if the current expansion rate continues and dark energy remains dominant. And as far as we can tell, that is exactly what will happen. Dark energy shows no signs of weakening. The expansion shows no signs of slowing. If anything, the acceleration is increasing. The universe is not just expanding, it is expanding faster and faster, and that acceleration is the thing that drives the fading. Without acceleration, distant galaxies would still recede, but their light would remain detectable for much longer. With acceleration, the light gets stretched so quickly that galaxies disappear on timescales that are short by cosmological standards. 100 billion years sounds like a long time. It is a long time. But it is not that long compared to the lifetime of a low-mass star, which can burn for 10 trillion years, or the lifetime of a white dwarf, which can glow faintly for 100 trillion years before cooling completely. The universe will still be full of stars when the last distant galaxy fades from view. It will just be full of stars that cannot see each other. The loneliness of that future is hard to overstate. Imagine living in a galaxy where the entire observable universe consists of your galaxy and nothing else. No external reference points, no other galaxies to study, no way to measure the large-scale structure of the universe because there is no large-scale structure visible. No way to test cosmological models because all the evidence is gone. You would have access to the stars in your own galaxy, sure, and you could learn a lot from studying them. You could measure their compositions, their ages, their motions. You could build models of stellar evolution and galactic dynamics. But you would have no way to know that your galaxy is just one of trillions, that it formed from the merger of smaller galaxies billions of years ago, that it is part of a vast cosmic web stretching across hundreds of millions of light years. You would be cosmologically isolated, cut off from the rest of the universe, not by distance but by the expansion of space itself. And you would not even know what you were missing. We are living in a unique era. The universe is old enough to have developed complexity. Galaxies, stars, planets, life, civilizations capable of asking questions about where they came from and where they are going. And the universe is still young enough that the answers are visible. We can still see the cosmic microwave background. We can still detect galaxies billions of light years away. We can still piece together the history of the universe from the light that has reached us. We can still test theories, make predictions, and compare those predictions to observations. Future civilizations will not have that luxury. They will inherit a universe that looks small, simple, and static, and they will have no way to know that it was once large, complex, and dynamic. The evidence will be gone, stretched into wavelengths too long to detect, scattered across distances too great to bridge. The universe will still exist in all its vastness, but it will be invisible, hidden behind the cosmic event horizon, as unreachable as if it had never been there at all. This is the dark future of the cosmos, not a future where the universe ends in fire or ice, not a future where everything collapses back into a singularity or tears itself apart in a big rip. Just a future where the universe keeps expanding, keeps accelerating, keeps fading, until the only thing left visible is the small patch of space we are gravitationally bound to. The local group, our island in the void, will become the entire observable universe. Everything else will have vanished, not destroyed but simply moved beyond the horizon, carried away by the expansion of space faster than light can follow. And the astronomers of that future, if they exist, will look up and see an empty sky and conclude that they are alone. They will be wrong. The universe will still be full of galaxies, trillions of them, just as full and just as active as it is today. But those galaxies will be invisible, lost behind the horizon, separated by gulfs of space so vast and expanding so fast that no signal, no probe, no message will ever cross them. The universe will still be there, but it might as well not be. It will be unreachable, unknowable, gone. And here is the truly uncomfortable part. This is not just a hypothetical future, it is already starting. The cosmic event horizon is already shrinking. Galaxies are already slipping beyond the boundary. Light from the most distant galaxies is already fading. We are already losing pieces of the universe, one galaxy at a time, and the rate is accelerating. 1 billion years from now, astronomers will have access to less information than we do. They will see fewer galaxies, detect fewer photons, and have a harder time reconstructing the history of the universe. 10 billion years from now, the observable universe will be noticeably emptier. 100 billion years from now, it will be almost completely dark. The process is slow by human standards, but it is happening, and it is irreversible. The expansion of space is not something you can turn off or slow down or reverse. It is built into the fabric of the universe, driven by dark energy, and as far as we can tell, it is permanent. The fading is not just about losing distant galaxies, it is also about losing context. Every galaxy we can observe adds to our understanding of how the universe works. Every measurement of a distant supernova refines our models of dark energy. Every observation of the cosmic microwave background constrains the parameters of the Big Bang. Every detection of a high redshift galaxy tells us something about the early universe, about how the first stars formed, how the first galaxies assembled, how structure grew from the tiny fluctuations imprinted in the first moments after the Big Bang. Lose those observations and you lose the ability to test those models. You lose the data that lets you distinguish between competing theories. You lose the evidence that tells you whether the universe is flat or curved, whether dark energy is a cosmological constant or something more exotic, whether the Big Bang really happened the way we think it did. Future astronomers will be left with a small, local sample of stars and gas, and they will have no way to know whether the patterns they see in that sample are universal or just local quirks. They will be doing science in a dark room with no windows, and they will not even know the room used to have windows. The realization that the universe is fading, that the observable universe is shrinking, that most of what we can see is already lost, is one of the most profound and unsettling discoveries in modern cosmology. It means we are living in a privileged time, a brief window when the universe is both old enough to be interesting and young enough to be visible. That window is closing, not tomorrow, not in a century, not even in 1,000,000 years, but it is closing, and once it closes, it will never reopen. The universe will continue to exist, continue to evolve, continue to be full of stars and galaxies and structure. But it will be invisible to anyone living inside the local group, hidden behind the cosmic event horizon, separated by an ever-widening gulf of space that no technology, no matter how advanced, will ever be able to cross. The universe will still be there, but it will be unreachable, and that makes all the difference. The fading lights are not a sign that the universe is ending. They are a sign that the universe is running away, and it is running faster than we can follow. We have just watched the lights go out. One by one, galaxy by galaxy, the universe is fading from view, not because the stars are dying, though that is happening too, but because the space between us and everything else is stretching so fast that the light gets pulled into wavelengths we cannot detect. We have seen how the cosmic event horizon is shrinking, how galaxies that were once visible are slipping beyond the boundary, how future astronomers will inherit a smaller, darker, lonelier universe than the one we see today. We have walked through the mechanics of it, the physics, the math, the inexorable acceleration driven by dark energy. We have established the facts. Now we need to sit with what those facts mean. Because the universe is not just fading, it is leaving, and most of it is already gone. Let me restate the situation plainly so there is no ambiguity. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is roughly 93 to 94 billion light-years across. That number accounts for the expansion of space over the 13.8 billion years since the universe began. The radius, the distance from Earth to the edge of that sphere, is about 46 to 47 billion light-years. Inside that sphere, astronomers estimate there are roughly 2 trillion galaxies, each containing anywhere from a few million to several trillion stars. The total number of stars in the observable universe is somewhere around 10 to the power of 24, a 1 followed by 24 zeros. That is more stars than grains of sand on every beach on Earth, more stars than seconds have passed since humans first learned to make fire, more stars than neurons in every human brain that has ever existed, combined. The observable universe is incomprehensibly large, and it is full, absolutely packed with structure and light and matter and energy, and most of it is unreachable, not because we lack the technology to get there, not because we have not built a fast enough rocket or a powerful enough telescope. We are cut off by the geometry of space-time itself. The expansion of the universe, accelerating under the influence of dark energy, has carried the vast majority of galaxies beyond the cosmic event horizon, the boundary beyond which light emitted now or in the future can never reach us. The figure that gets repeated, the one that has made its way into headlines and videos and public talks, is 97%. 97% of the galaxies in the observable universe are already beyond the horizon. We can still see them, but only because we are looking at the past. The light hitting our telescopes tonight left those galaxies billions of years ago when they were closer and the expansion was slower. The galaxies as they exist right now, in the present, are farther away, receding faster, and completely out of reach. No signal we send will ever catch them. No probe we launch will ever arrive. They are gone, not destroyed, not erased, just moved beyond the point where cause and effect can connect us to them. They are still out there, still glowing, still full of stars and planets and possibly life, but they exist in a part of the universe that is no longer part of our universe in any meaningful sense. They are on the other side of a line we cannot cross. 97%. Think about that number for a second. If you could somehow catalogue every galaxy in the observable universe, write down their names, their distances, their masses, their ages, and then mark which ones are still reachable and which ones are not, you would find that only 3% are still inside the boundary. 3%. The rest have slipped away, and the boundary is still shrinking. Every second, more galaxies cross the line, more information is lost, more of the universe becomes inaccessible. The expansion is not slowing down, it is speeding up. And as long as dark energy remains dominant, which appears to be the case for as long as we can project forward, the horizon will keep shrinking. Future civilizations, if they exist, will have access to even less than we do. They will see fewer galaxies, detect fewer photons, and have a harder time reconstructing the history of the cosmos. Eventually, billions of years from now, the only galaxies visible will be the ones in our gravitational neighborhood, the local group. Everything else will have faded beyond detectability, erased not by any physical process, but by the relentless stretching of space. This is not a technological limitation, it is a fundamental one. You cannot build a telescope powerful enough to see beyond the cosmic event horizon because there is no light from beyond the horizon that will ever arrive. The photons are out there, traveling through space at the speed of light, aimed in our direction, but the space between us and them is opening faster than they can cross it. They are running on a treadmill that is accelerating away from them, and they will never catch up. This is not a problem you can solve with better engineering or more funding or a few more centuries of scientific progress. It is written into the structure of the universe itself. The edge of the observable universe is not just an observational boundary, it is a causal boundary, a line that separates the part of the universe we can interact with, even in principle, from the part we cannot. And the line is moving, not toward us, away from us. The philosophical weight of this is hard to overstate. For most of human history, the universe was assumed to be either small and geocentric, with Earth at the center and the stars fixed on a celestial sphere, or infinite and eternal, stretching out forever in all directions with no beginning and no end. Both pictures were wrong, but they were at least conceptually stable. The geocentric model was cozy, everything revolved around us. The infinite eternal model was vast, but at least it was comprehensible. If the universe is infinite and eternal, then everything that can happen will happen somewhere, sometime. There are no edges, no boundaries, no limits. You can always go farther, look deeper, find more. The modern picture is stranger. The universe is neither small nor infinite in the way those old models imagined. It is large, almost unimaginably large, but it has a boundary. Not a physical edge where space stops, but an observational edge where the light stops reaching us. And that edge is not fixed, it is shrinking. The universe is not just big, it is also temporary. The view we have right now, the galaxies we can see tonight, the cosmic microwave background glowing faintly in the radio spectrum, all of it is transient. It is here now, but it will not be here forever. The universe is not winding down towards some stable equilibrium. It is running away, and it is taking most of itself with it. This is what astronomers mean when they talk about the unreachable universe. Not the part we have not reached yet, but the part we can never reach, even in principle. The part that is already beyond the boundary, where physics allows any kind of interaction. The observable universe is a bubble, and we are sitting inside it, watching it shrink. Not because the bubble itself is collapsing, but because the space outside the bubble is expanding so fast that the light from farther out cannot keep up. The bubble is defined by light travel time and the expansion history of the universe. It is a temporary window, a brief moment in cosmic time when the evidence is still visible, still detectable, still within reach. That window is closing. It has been closing since the moment the universe started accelerating, roughly 5 billion years ago, and it will keep closing for as long as the acceleration continues, which, as far as we can tell, is forever. The idea that infinity has an edge sounds like a contradiction. Infinity, by definition, has no edges. It goes on forever. But the edge we are talking about is not an edge of the universe itself. It is an edge of what we can observe, an edge that depends on where you are standing and how fast space is expanding around you. Every observer in the universe, no matter where they are, sees their own cosmic event horizon. An observer in a galaxy 10 billion light-years away from us would see a different horizon than we do. They would see galaxies we cannot see, and they would not be able to see some of the galaxies we can see. Every location in the universe has its own observable bubble, its own temporary window, its own shrinking horizon. The universe as a whole may be infinite, or it may be finite but much larger than the part we can observe. We do not know, we cannot know. All we can see is the bubble we are trapped in, and that bubble is not showing us the whole picture. It is showing us a local view, a snapshot, a piece of something much larger that we will never have access to. This is profoundly humbling. Not in a poetic, feel-good way, but in a way that forces you to recalibrate your sense of scale and importance. We are sitting on a planet that is 4.5 billion years old, orbiting a star that is middle-aged and unremarkable, in a galaxy that contains hundreds of billions of other stars, most of which probably have planets, in a local group that contains a few dozen galaxies, in a universe that contains 2 trillion galaxies, 97% of which are already out of reach. We are not at the center. We are not special in any cosmological sense. We are not even in a particularly interesting part of the universe. We are in a spiral arm of an average galaxy in an average cluster on the outskirts of an average supercluster in a universe that is so large and so old and so indifferent to our existence that it has already moved most of itself beyond the point where we could ever interact with it. We are not the main character. We are not even a supporting character. We are an extra in a background shot, and the camera has already moved on. And yet, here is the thing. We are also the only observers we know of. The only species, the only civilization, the only collection of matter that has figured out how to look up, measure distances, calculate expansion rates, reconstruct the history of the universe, and realize that most of it is already gone. That is not nothing. The universe does not care that we are here. It does not care that we are asking questions. It does not care that we have built telescopes and satellites and particle accelerators and written equations and tested theories and slowly, painstakingly, over the course of centuries, pieced together an understanding of where we are and how we got here. But we care. And the fact that we care, the fact that we are capable of caring, the fact that we can look at a galaxy 10 billion light-years away and calculate when the light left and how fast the galaxy is receding, and whether we will ever be able to reach it, is remarkable. It is the only remarkable thing about us from a cosmic perspective. We are not special because of where we are. We are special, if we are special at all, because of what we can do. We can observe, we can measure, we can think, and right now, in this brief window of cosmic history, we can still see enough of the universe to understand what we are looking at. That window is temporary. We have talked about this already, but it is worth repeating because the implications are so strange. The observable universe is not a fixed thing. It is not a permanent feature of reality. It is a transient phenomenon, a bubble of space from which light can currently reach us, and that bubble is constantly changing. New light is arriving from farther and farther away as photons that have been traveling for billions of years finally complete their journey. But at the same time, galaxies that were once visible are fading from view as their light gets stretched beyond detectability. The net effect, over billions of years, is that the observable universe is shrinking, not in radius, which is still growing slowly, but in content. Fewer galaxies, fewer photons, less information. Future astronomers will inherit a universe that looks smaller, simpler, emptier than the one we see today, and they will have no way to know what they are missing because all the evidence will be gone. This is the edge of infinity from our perspective. Infinity, the actual universe, the whole thing, whatever it is, wherever it extends, is still out there. It has not gone anywhere. It is not shrinking. It is not fading. It is just moving away from us faster than we can follow. The edge is not a physical boundary. It is a horizon, a limit imposed by the finite speed of light and the accelerating expansion of space. And that horizon is moving, not in space, but in time. Galaxies that are currently just inside the reachable region will slip outside it in the future. Galaxies that are currently visible will fade from view. The edge is advancing, closing in, cutting us off from more and more of the universe with every passing second, and there is nothing anyone can do to stop it. You cannot outrun the expansion of space. You cannot slow it down. You cannot reverse it. It is built into the fabric of reality, driven by dark energy, and as far as we can tell, it is permanent. So where does that leave us? Sitting on a rock orbiting an average star in an average galaxy, watching the universe fade, that is the cold, hard cosmological truth. But it is not the whole truth. Because while most of the universe is unreachable, some of it is not. The local group, our gravitational neighborhood, is still intact. The galaxies within it are not receding. They are orbiting, interacting, merging. We are still connected to them. We can still observe them. We can still, in principle, send signals to them, though those signals would take millions of years to arrive, and the civilizations that might receive them, if they exist, would not be able to send a reply that reaches us before the sun dies. But the connection is there. The light from Andromeda, 2.5 million light-years away, reaches Earth every night. You can see it with your naked eye if you know where to look, and the sky is dark enough. It is a faint smudge, barely noticeable, easy to miss. But it is there. A galaxy containing 1 trillion stars, sitting just far enough away that its light takes 2.5 million years to reach us, close enough that gravity still binds us together. That galaxy will collide with ours in about 4 billion years, and the two will merge into a single giant elliptical. And when that happens, the night sky will change, the stars will scatter, the spiral arms will dissolve. The structure we see now will be erased, but it will still be our neighborhood, our island, the raft we are lashed to in the expanding ocean of space, and that island, small as it is not nothing. The local group spans about 10 million light-years. It contains at least 50 galaxies, possibly as many as 80 if you count the faintest dwarfs. It contains hundreds of billions of stars, trillions of planets, and all of it is still reachable, at least in principle. You could build a ship, accelerate it to a significant fraction of the speed of light, aim it at Andromeda, and it would eventually arrive. Not in your lifetime, not in 1,000 lifetimes, but it would arrive. The connection is still there. The galaxies in the local group are not ghosts. They are not frozen in the past. They are present, active, evolving, and we can still observe them in real time, or at least as close to real time as the speed of light allows. 2.5 million years is not real time by human standards, but it is real time by cosmological standards. Andromeda as we see it tonight is only 2.5 million years out of date. That is recent. That is practically current. Compare that to a galaxy 10 billion light-years away, which we are seeing as it existed when the universe was only a quarter of its current age, and you realize how lucky we are to have neighbors at all. The observable universe, even in its current state, even with 97% of it already beyond reach, is still vast, still beautiful, still full of structure and complexity and mystery. We can still see the cosmic microwave background, the faint afterglow of the Big Bang, glowing uniformly in all directions. We can still detect galaxies whose light has been traveling for more than 13 billion years. We can still map the large-scale structure of the universe, the cosmic web, the filaments and voids that stretch across hundreds of millions of light-years. We can still measure the expansion rate, test cosmological models, and refine our understanding of what the universe is made of and how it has evolved. We are living in the golden age of cosmology, the brief window when the universe is both old enough to have developed complexity and young enough that the evidence is still visible. That window is closing, but it is not closed yet. We still have time. Not infinite time, but enough time to ask the questions and, in some cases, find the answers. There is a perspective shift that happens when you internalize the scale of the unreachable universe. At first, it feels like a loss. You realize that most of the universe is already gone, that the boundary is shrinking, that future astronomers will see less than we do, and the instinct is to mourn what is being lost. But the longer you sit with it, the more it starts to feel like the opposite. Not a loss, but a gift. Because we are here, right now, in this moment, in this narrow slice of cosmic time, when the universe is still visible, still observable, still full of light and structure and information. We did not have to be here. The odds against any particular configuration of matter waking up and asking questions are astronomical, and yet here we are, standing on a planet that is stable enough and old enough to support complex life, orbiting a star that is neither too hot nor too cold, in a galaxy that is neither too chaotic nor too dead, in a universe that is neither too young to have structure nor too old to still be visible. We hit the jackpot, not because we are special, but because we are lucky. Lucky to be here, lucky to be now, lucky to have eyes and brains and instruments and the ability to look up and see the universe before it fades. The edge of infinity is not a wall, it is a horizon, and horizons, by their nature, are always just out of reach. You can walk toward a horizon for your entire life and never get any closer because the horizon moves with you. It is defined by your position, your perspective, your limitations. The cosmic event horizon is the same. It is not a fixed feature of the universe. It is a feature of our relationship to the universe, a boundary imposed by the fact that we exist at a particular place and time, and the laws of physics constrain how far we can see and how far we can reach. Move to a different place, and the horizon moves with you. Wait 1 billion years, and the horizon shrinks. The edge is not out there in space. It is here, in the relationship between where we are and where everything else is going. And that relationship is changing. The universe is not static. It is not stable. It is expanding, accelerating, running away, and taking most of itself with it. The observable universe is shrinking in content even as it grows in radius. The galaxies we can see are fading. The cosmic microwave background is redshifting into undetectability. The evidence is disappearing, and when it is gone, it will not come back. There is no second chance, no do-over, no future technology that will let us recover the information that has already been lost. Once a galaxy slips beyond the horizon, it is gone. Once the cosmic microwave background redshifts below the noise floor, it is gone. Once the last photon from the early universe arrives, it is gone. The universe is not repeating itself. It is not cyclical. It is not giving us infinite opportunities to observe and measure and understand. It is giving us one shot, one window, one brief moment when the lights are still on and the view is still clear, and we are living in that moment right now. So what do we do with that? How do you live in a universe where 97% of everything is already out of reach and the rest is fading? How do you make sense of a cosmos that is so large you cannot comprehend it and so temporary you cannot hold on to it? The answer, I think, is that you do not try to comprehend all of it. You cannot. No one can. The universe is too big, too old, too complex, too indifferent. But you can comprehend the part you have access to. You can look at the stars in the night sky and know that some of them are closer and some are farther away. You can look at Andromeda and know that it is a galaxy like ours, full of stars and planets and maybe life, and that it will collide with us in 4 billion years. You can look at the cosmic microwave background and know that it is the oldest light in the universe, stretched and cooled by 13.8 billion years of expansion, and that it will not be detectable forever. You can look at the farthest galaxies we can see and know that they are already gone, that we are looking at their past, that the present is out of reach. You can know all of that and still appreciate what you have. The observable universe, small as it is compared to the whole, is still incomprehensibly large, still full of wonders, still full of things we do not understand and questions we have not answered, and it is still here, for now. The edge of infinity is where we live. Not at the edge in the sense of being on the boundary, but at the edge in the sense of living in a time and place where the boundary matters, where the limits are visible, where the horizon is close enough to see and far enough away that we have not crossed it yet. We are living in the last era when the universe is still fully observable, still fully knowable, at least in principle. Future civilizations will not have that. They will inherit a smaller, darker, lonelier cosmos, and they will have no way to know what they are missing. But we know. We have the data. We have the telescopes. We have the equations. We have looked out as far as we can see and measured what is there and calculated what is beyond and realized that most of it is already gone. And that knowledge, uncomfortable as it is a privilege because it means we understand our place. We know where we are, how we got here, and where everything else is going. We know the universe is vast and we are small. We know the universe is temporary and we are even more temporary. We know that the lights are fading and the horizon is shrinking and there is nothing we can do to stop it. And we know that none of that diminishes the fact that we are here, now, in this moment, looking up at a sky that is still full of stars. That is our place in the unreachable universe, not at the center, not at the edge. Somewhere in the middle, on a small rocky planet, in a quiet corner of an average galaxy, watching the rest of the cosmos run away. It is not a heroic position. It is not a dramatic position. It is not even a particularly interesting position by cosmic standards, but it is ours. And for a brief, improbable moment in the history of the universe, it is enough. So here we are, standing on a planet that orbits an unremarkable star in an average galaxy, looking out at a universe that is 94 billion light-years across, and realizing that 97% of it has already slipped beyond the edge of forever, not destroyed, not erased, just moved, carried away by the expansion of space faster than light itself can follow. We can still see those galaxies, but only because we are looking at ghosts. The light hitting our eyes tonight left them billions of years ago when they were closer and the universe was younger. The galaxies as they exist right now, in this moment, are gone. We will never know what they look like today. We will never receive another photon from them. They are on the other side of a line we cannot cross, separated from us not by distance but by the geometry of space-time itself, and the line is moving. Every second, more galaxies slip across the cosmic event horizon, more light fades into wavelengths we cannot detect, more of the universe becomes unreachable. The observable universe is not a fixed thing, it is a temporary window, and that window is closing. Future astronomers will inherit a smaller, darker, lonelier cosmos than the one we see tonight. They will look up and see one galaxy surrounded by emptiness, and they will have no evidence that anything else ever existed. The universe will still be there, still vast, still full of stars and structure, but it will be invisible, hidden, lost behind a horizon that no technology will ever let them cross. We are living in the last age when the universe is still visible,